Welcome to another coding session. I'm Marcel. I'm working on a new programming language called Plum. Yeah, it looks like this. Last session we introduced lambdas or closures. So this, for example, is a function call to the function make incrementer, which is defined down here. It takes an a, which is an int, and it returns a function that maps integers to integers. Yeah, they look like this with a backslash, and it returns a function or lambda that takes another argument b and then returns a plus b. So basically here we create a function that always increments the input by 3. And then we call that resulting function with 3, and that should hopefully result in 8. Yeah, so this compiles the compiler now. And now the compiler compiles the program, and yeah, we get 8 as a result down here. So yeah, we already do like all of the type checking and so on. Plum is a statically typed language, so here we call the make incrementer function, and we track that this returns a lambda that maps ints to ints. So we know the type of every single expression at compile time. Yeah. And I basically want to use that to decide on efficient memory layouts, which is something that we don't do currently. So yeah, currently our objects, the values that we create, they are represented like this. We have this universe of objects, which is just a list of objects. And this is an enum that says it's either an integer, or it's a string, or it's a struct, and so on. And the representations of these, they are quite inefficient because they don't use the type information at all. For example, for a struct, even though if we create a struct, which by the way looks like this, let's say point is a struct with 2 fields, x and y, they are both integers. And we see that something, I don't know, returns a point. We could just make this function like return 2 integers. But what we actually do is it returns an object of the type struct, which then contains a map that maps x to an index into this list that is then an int, and that maps y to another index into this list that is also an int. Obviously, this is not efficient, and this is something that we need to change in the long term. Okay, yeah, I've recently been reading this this interesting paper about the dangers of abstractions. So usually abstractions are nice because you don't have to think about the underlying implementation, and you can just reuse code easily. But this paper argues that the abstractions that we have created as a software engineering industry make it difficult to drop into lower levels of abstractions and to like really understand what's going on in the paper. And what they do is they basically create a new programming language from scratch, like from x86 machine code. Not even assembly, but machine code directly. So in their language, they don't hide the underlying bytes that the CPU knows how to execute, but they have them in their program. And the actual instruction names and so on, they are more like comments that come afterwards. I just thought this was an interesting take. Not that I agree with this, I think for bigger software projects, you have to do a lot of mental bookkeeping to make this worthwhile, to make this practical, basically. You don't want to think about which register do I use for this variable and so on. Yeah, but still, very interesting, and it kind of got me in the mood for some low-level stuff. And that's why we're going to look at memory layouts today. Okay. Yeah, how do we improve memory layouts, and why is that even important? So modern computers basically consist of two components, like at least two components related to the actual computing of stuff. And these two most important components are the CPU and memory. The CPU can do calculations like add numbers and so on. And it has only a very limited set of registers, of values that it can keep track of. If you want to store more things, like, I don't know, entire files containing code or like anything really, you need to go to this RAM or memory that is a lot bigger. And that is usually the bottleneck in like most applications that you run. If you do some crazy simulations or calculations or, you know, scientific stuff, sure, like the CPU can still be a bottleneck. But usually the CPU utilization is quite low, and memory, especially memory latency, is the thing that affects how performant your programs feel. So we want to minimize the things that we read and write from memory. We want to minimize the things that go from CPU to the memory component and back. And one way to do that is to have something more efficient than this. You know? Right. Yeah, let's maybe talk about how memory layouts for statically typed languages work. So if you, I don't know, write some program in C and you have some struct, then the compiler will decide how this struct is represented. Like, this struct has a size of, I don't know, 64, of like 8 bytes in memory, I think. And because ints usually have 4 bytes in C. So we have these 4 bytes containing the first int, and then perhaps a second part of 4 bytes that contains the second int. And when you access the underlying fields of a struct, really the compiler can convert this into just, you know, loading or copying the parts of the struct. So here, for example, we allocate some memory for that struct. So we allocate 8 bytes in this case. And then here we set the fields of the struct. It's basically the same as, you know, copying the value of this, or in this case, like copying the 2 somewhere into memory, into some 4 bytes that are at the address, you know, captured plus, what is it, plus 4. Like, you could just as easily write this. And I think this is, no. Oh yeah, the typing kind of goes, gets in the way here. I think we can do this, maybe. Oh yeah, we need to cast that to an int pointer like this. Yeah, okay. So we have our captured thing, which is a pointer to this struct. And the pointer casts, they don't do anything, you know, we just say, hey, just ignore what it points to. And then we increment 4, which is the offset of the B inside of the struct, because the A is 4 bytes. And the B is 4 bytes. So if our struct here, captured, is at, I don't know, let's say incrementer captured, if that is at address 1, 2, 3, 4, 5, 6. Let's do it in decimal. Then the A field, you know, is also at that same address. So structs don't introduce any overhead. You know, it's really just these two ints being next to each other in memory. And the, hang on, B field is at 60, something like this. So basically, each of these struct accesses, they don't, hang on, they don't look something up in a hash map or something at runtime, because that's like really efficient. You have to compute the hash of a string and then walk the entries of the map or the buckets and look for a matching key in there. And like that's hugely inefficient code. What you really want to do is just say, okay, we know where our struct is saved in memory. We have the address of that. So now let's add 4 to that. And we immediately know where the second field is saved. Yeah. And as you might imagine, like this is also a lot more efficient in terms of memory usage. You know, if you have your memory that is 8 bytes, that's a lot less than storing strings and lists of entries and stuff like that. Yeah, so it's because we are a statically typed language, so we know the types of all of our expressions, we could theoretically, like C, decide on memory layouts up front and then use those later on. Yeah, so this is what we're going to do. Instead of having this, enum that the Martinaise compiler, the host language compiler basically implements in some magic way, we will write this ourselves. Okay, so let's maybe talk about memory layouting, I think. Yeah, I'm gonna switch to my iPad. Okay, so we have some memory, which is basically you can think of it as a linear set of bytes that we can read from and write to. And now we want to decide how to store things in that memory. And basically, it depends on the type of object that we have. In Plum, our language, we have, let me just get the types for reference. Yeah, we have different types. We have ints, we have strings, we have structs, we have enums, we have lambdas, and that's it. Okay, so we basically need to decide how to represent each of them in memory and basically have a strategy for representing values of those types. Yeah. Okay, so integers, I think we will just take a very similar approach to what Martinaise does, which is just have 8 bytes for them, 64-bit integers. So an int is just 8 bytes, and in here one square in here is 1 byte. So yeah, this would be an integer. Strings will also be similar to Martinaise. So it's basically a tuple of a pointer and the length of the string. Why do we do it like this? And why not just have the actual string bytes in here, like, I don't know, hello. The thing is that we want these memory layouts to be known at compile time. That's what this entire thing is about. That we don't look something up in a map, or that the actual values that are saved, they can't affect the layout of those types. So that if we have a struct, for example, we can just say struct address plus 5 or plus 8 or something to get to a specific field, because we know how big all of the fields are without looking at the values, just by looking at the types. All right, so each type, maybe let's write that down. Each plum type has a memory layout with a known size. Yeah, that's basically the idea of making memory things efficient. Okay. So yeah, that's why we don't do this, but instead we have a pointer that points to somewhere in memory, where then the actual string data is stored. Yeah, that means, that basically means that if we have a struct, for example, and the first field is a string and the second field is an integer, then we can just say, struct address plus 16, because we know that strings are always 16 bytes long, to get to that integer. It doesn't depend on the actual string that's saved there. It makes a lot of other things a lot more sane if you have fixed sizes per type. Okay, so we have a strategy for ints and strings. Next, structs and enums. And these are a bit more difficult, because here we don't want a fixed memory layout for all structs. That would basically be similar to what we have currently with our map from string to field. But what we want is for each struct type to compute a new memory layout for that. So for example, if you have a point defined as a struct looking like this, with int and another int, then we want the memory layout of that to be this. Just the first int in memory, followed by the second int in memory. And these would be x and y. Yeah, that's the plan. And like for each type that you have, each struct that you have, we then decide on a new memory layout for that. Okay, yeah, seems reasonable to me. One more thing I should mention is that currently we don't have types that are smaller than 8 bytes, but assume we also have a byte type like this. That's just a single byte. Memory is a bit more peculiar than you might think. So you can read anywhere from memory, like reading a byte from, I don't know, address 1 to 3. Like let's say something simpler, address 13. You can also read 8 bytes simultaneously, basically. Because the way that CPUs work is you have your CPU, which has these internal registers, which it uses to actually do calculations. And then, so for example, in order to add two numbers, you would read one number into one register, and then read another number into a register, like this, and then you would add them together in these registers, and then write that out to memory again. Write 8 bytes. And to do that efficiently, there's not just read byte, which reads a single byte, but read 8 bytes, and also read 2 bytes, read 4 bytes. Maybe read 60 bytes, I'm not sure about that. But basically there are these reading operations for bigger numbers, basically, which then read an entire section of memory, like 8 bytes. And the difficulty with that is that they have different performance characteristics based on the alignment. So what's alignment? Memory, I don't want to go into how memory is implemented, but the gist is this, that reading and writing from addresses that are a multiple of some value is more efficient than reading from addresses that are not a multiple of that. So if you have, if you read from address 13, that may be less efficient than reading from address 24. And same for writing. So the way that most memory works is that these reads and writes of 8 bytes, the address should be aligned to a multiple of 8. So the absolute address should be a multiple of 8. That's a bit crazy or a weird limitation if you think about it. But apparently it makes sense from the implementing the memory bus, memory things. So yeah, that's kind of the hardware that we are stuck with, the hardware that we're targeting. Yeah. Okay. Yeah, which means it's kind of difficult to lay out structs sometimes. Because let's assume, let me remove this red line. Yeah. Let's assume that we have some struct that contains, I don't know, an x, which is a byte, and a y, which is an int. If we put them in memory next to each other, like this, x and then y, from a memory utilization perspective, this is pretty efficient. Like all of them are packed together. But when we actually access the fields, like we say, I have some foo, and then I access the y thing. This is not as efficient as it could be, because let's say that this happens to be 8 byte aligned. I don't know, address, let's say address 24. Then this will try to read an 8 byte, basically do this, read 8 bytes from address 25, which is not efficient. So really when allocating memory and when deciding where to store things in memory, we also need to make sure that all of the integers, they are at multiples of 8 bytes, which is weird. But other languages do that as well, by the way. It's not like this is something unique to Plum or something. And the way they do that is that they introduce padding. They are intentionally wasteful with memory. So, for example, in C, if you have a struct containing a byte and an integer, then the underlying C struct will actually look like this. You will have the x, the byte, then you have just garbage in memory somewhere, and then afterwards, at 8 bytes aligned, you have the actual y field, like this. So in C, the malloc function, to allocate memory, it expects a size and an alignment, which basically says how, by which number should the memory be divisible by the address that I give you. And this defaults to 8 bytes. So malloc always returns you an address that is divisible by 8. You can specify something less, and you can also specify something more. And again, that depends on the platform, how well those are respected and so on. But it is kind of crazy. You have a struct containing a byte and an int, and you would assume these are just 9 bytes, but in fact they are 16 bytes big, because there are like 7 bytes of garbage in here. Yeah, which means that when deciding on a memory layout for a struct, we basically don't just want to result in a plan for how we save things and have a size basically based on that, but we also want to say, hey, this is the memory layout and this is the alignment that it requires. So for the byte, the alignment is 1. For an int, the alignment is 8. For a string, it's also 8 because it contains an int, then n, and also pointers should also be aligned to 8 bytes. And in this case, because it contains ints, and this int has an alignment of 8, and this int also has an alignment of 8, the entire thing also has an alignment of 8. Which means that such a struct should only be placed in memory at positions that are a multiple of 8. There are structs where that's not the case. If we had a struct that contains a byte and another byte, then this would just be like 2 bytes next to each other, and they can be stored anywhere. So it's not like the alignment is a multiple of is in any way related to the size. We could just have a struct containing like 16 separate bytes, and we would treat that differently than a struct containing 2 ints. We are more flexible with a struct where you only access individual bytes than a struct where you want to read and write entire ints. Because for the int containing structs, we want to ensure that the reads and writes are efficient. Okay, yeah, so we have this concept of padding in here, and we have the concept of struct fields. Now for the kind of sad part. This can become really, really complex. I'm just going to say that right now, because let's say you have a struct that contains 3 fields. It contains x, which is a byte. It contains y, which is an int. And it contains z, which is a byte again. The packed version of this, like packing everything together, would look like this. You have x, y, which is 8 bytes, and then z, which is 1 byte. But of course, that's inefficient. So what the C compiler does is this. We have the x, then we see, okay, the next thing should be y, which is an integer, which should be aligned to 8 bytes. So we need to introduce padding, like we did up here. So just some garbage in the struct, and then we have another 8 bytes containing y, and finally a single byte containing z. This is actually what C code does. If in C you declare a struct like that, this is how it's going to look. And some other compilers, like the Rust compiler, and I think also the Zig compiler, they reorder fields to make things more efficient. So in this case, for example, we could say that actually in memory, the z comes first. Like this, we have x, then we save the z directly in here. we only have 6 bytes of garbage in here, and then we have our y. Yeah. And it's non-trivial to find efficient memory layouts for structs. Or at least, I think it is. I'm not entirely sure. Yeah, and we need to deal with that. Fun. Really, really fun. Yeah. By the way, some languages, I'm not even sure if languages, some languages require that the size of a type is a multiple of its alignment. So because here we just disregard alignment completely, but in this case, because the alignment is 8, because of the y field, we want to access that efficiently. That means that the size of the struct also has to be a multiple of 8, which means we have an additional garbage part at the end. Some languages do this, others don't. I'm not sure what I'm going to do. And I'm actually not sure what kind of languages take what approach, which is interesting. You know what, let me switch back to the PC and just try things out. Yeah, I'm just going to create, I guess, a struct in Rust. Struct foo contains an x, which is a use size, which is 64 bits, so 8 bytes. And when we hover over that, I think you can actually see the size somehow, sometimes. Okay, we do have tooling. Or does it actually have to be used somewhere? Like this. Like foo with x 1 by 2. Nope, not getting any information here. That's weird. Let me maybe, or maybe because things don't compile anyways, because I removed stuff. That maybe it. No, just doesn't do that. Huh. I could have sworn I've seen some memory layering things in other projects. Let me maybe open like a real Rust crate thing I had. Yeah. Sure. Okay, at least it says loading, so I think that's good. But yeah, it's still, yeah, Rust compiler doing Rust things. Okay, yeah. Nice. Here we can see that the size of the struct is 72 bytes, quite a lot, and that the alignment is 8 bytes. So this struct can only be stored at, or should be stored for efficient access at addresses that are a multiple of 8. And let's maybe create our struct containing foo. Let's maybe be efficient, explicit. So we have something that is 64 bits, aka 8 bytes. And we can see that the entire struct has a size of 16 bytes. 8 bytes plus 8 bytes makes sense. But now, what if we change the first one to a U8? Oh, look at that. The size is still 16 bytes. What if we change the second one to 32? Now the second one is 4 bytes, which means that the alignment of the entire thing needs to be by 4 bytes. But the size is still 8, because now we have 1 byte for this, and basically 3 bytes of garbage, and then another 4 bytes for the second field. And just to show you that C layouts this efficiently, I'm going to add another byte here. And you might think, okay, now the struct gets bigger, but no, it doesn't, because the Z is sorted before the Y in memory. So in memory we have, I'm not even sure, we may have X and then Y and then some garbage and then X and Z and then some garbage and then Y. But we may also have Y first and then X and Y, X and Z. You don't know what the memory layout of this is going to be, and you are not supposed to rely on that. If you really want to rely on that, you would have to, oh, there was some way to tell Rust to have the C representation. I think it's like this, wrapper C. Yeah, now the struct will have the same layout as C structs. Look at that, the size increased from 8 to 12. Because now we have 1 byte, then 3 bytes of garbage, of padding, you know, then 4 bytes, and then another byte, and then again 3 bytes of garbage of padding. Yeah. And you can also see that the Rust compiler will always choose a size that's a multiple of the alignment. So even if we have 8 bytes plus 1 byte, you might think, okay, that's like 9 bytes. No, it's 16 bytes, because in Rust the size is always a multiple of the alignment, and the Rust compiler does that to make things easier. Especially if you have multiple foos in memory next to each other, like you can have these slices in Rust, which basically says have U8s right next to each other in memory. If you do that with foo, those should all be aligned. Yeah, there are languages that don't do this, like my language Martinaise, which I just closed. It takes a different approach, where in the standard library we have, hang on, where is that, memory maybe? Oh yeah. Font size of. We do have some. Oh wait, there's an ASM module. Maybe it's here. Memory. Yeah, no, it's not. Where is it? Oh, in type. Well, of course. Okay, so in Martinaise there are different functions. There's size of, which tells you the size of a type. There's alignment of, which tells you, the alignment. These are similar to the Rust ones, but the size is not a multiple of the alignment. But there's a separate concept, which is the stride size, which is the size that you need to use if you want to store multiple of them next to each other. Yeah. And yeah, this is implemented like this. So it's just size of rounded up to a multiple of the alignment. Yeah. Okay, actually I'm wondering, like, if you nest structs, does that... Okay, I have an interesting proposition. What if you have a struct that contains a U64, so 8 bytes of memory, and then it contains one field, which is 1 byte. The size of the entire thing is still 16 bytes. But then if you have 2 of those in memory next to each other, will the Rust compiler, like, will it keep the things, the actual struct fields intact? Or will it try to merge them and basically have like one, merge the single byte from this struct field and the single byte from that other struct field? I think it will not merge them, but I'm not 100% sure on that. Yeah, I guess. Oh yeah, maybe I should have opened just this file. Oh, still works. Okay. Hang on, what did I want to do? Oh yeah, I have a second struct bar, and then I don't know, also contain things inside, but 2 foos. So this is 16 bytes big, and this is 32 bytes big. Okay, that makes sense. Yeah. Okay. Yeah. Okay. Hang on. Like if we have something like this, and then we have something that's just an option of that, which is Rust's version of being something that either doesn't exist or that contains the T. The size of this is still 16 bytes. Will the size of this be 24 bytes? Are you kidding me? That is quite a lot. Huh. Okay, so in my language, Martinaise, things are a lot more efficiently laid out. So let me maybe open, just open the folder and go. I thought we had a nice diagram somewhere. Oh yeah, here. So enums in this language are represented as first the payload of the enum, and then at the end 1 byte that is the tag that tells us which enum variant is it. And because our size doesn't have to be a multiple of the alignment, we can have a maybe of a string, for example. And that can be represented really efficiently because each maybe just adds a single byte at the end. But in Rust, that's not the case. In Rust, if you have, we had our foo type, which had an alignment of 8, and then we had a maybe of that. And even though there was garbage in the end at the struct, the maybe added another 8 bytes to that. Like each enum you have, each maybe adds another 8 bytes to that. That is super inefficient, I think. Interesting. No, I'm not gonna do that. I'll keep like a simple, predictable memory layout with a separate size and stride size, so that nested enums are represented efficiently as well. Okay, which kind of took. It was a bit of foreshadowing of how we're gonna save enums. So let me maybe switch back to market. Okay, so we saw that in, this is the approach that Rust chooses. But the approach that I want to choose is reorder the fields so that, hang on, maybe like this is the biggest, this is the perfect layout basically. We have the field X, the field Y, and then X and Z. And this entire thing is aligned to 8 bytes. Not to 16 bytes. Unlike Rust, we won't have garbage in the end, or we will have stuff like this. We have no garbage here whatsoever. Really efficient. And now if we have an enum of that, rather than having to add another 8 bytes to that, like the Rust enums, we just put a single byte after that that tells us, hey, which thing is it? yeah, I think that's a sane approach. Okay, so structs should be layouted in a very efficient way. Yeah, I should maybe note that size does not have to be a multiple of the alignment. Okay. Like these are like design decisions, you know, the box things. This and this, these are things that we just decide because they are practical and make things efficient. Okay, getting into enums. Let's say we have an enum, you know, maybe of foo. So maybe foo. And I should maybe remove the ones that we don't choose. This is something we don't choose because the y is not aligned. Like maybe, well, yeah, I'm just gonna cross out all of them. Maybe in a separate layer so I don't. Okay. So yeah, maybe like in general enums I think should have the payload. No. In our case that's foo. That we're just gonna draw as this. Yeah. Foo. Followed by the tag. The enum tag, which tells us which variant is it. And of course, only one enum variant can be active at a time. You know, if we have, I don't know, an enum true or false, very obvious, it's either true or it's false. And by the way, this doesn't have any payload, so it will just be a single byte, a single tag. There's either 0 or 1. If we have payloads, however, you know, let's say we have an enum that is either foo with an int or bar with an int, or let's say, yeah, with an int. Then we basically want this layout. Undo is kind of, well, yeah, we want this layout where this is the int and this is the tag. And we only need a single int because we know that only one variant is active. So foo would just be tag 0 and then here, you know, a 5 maybe. So foo 5 would be that. Or bar 3 would be int 3 and then in here the tag 1. And if they have different sizes, you know, like this is a byte, then for the bar, we still need to fill all of that space with something. You know, that's our thing here. Each type has a memory layout with a known size, independent of the value. So, so we somehow need to put something in there. So let's maybe, yeah, let's maybe draw this as just having a payload. Payload, we don't know which one it is, you know. And then depending on the tag, the payload has different memory layouts. If the tag is 0, then the payload will have this layout. Just, you know, being in it. If the tag is 1, then we still need to fill that payload thing, but it will just be a single byte. And then padding. Yeah, I think that's a sane approach. Cool. Very, very cool. Yeah, I like that. I like that. I should maybe note that I want Plum to be a language that can be embedded into other languages. So, you have your, you can implement a bytecode interpreter in Rust or C or Zig or JavaScript or Python or anything. And then you can run your Plum programs, and they can't have any side effects. They just return values, and then you can they can return values, including lambdas or like continuations, what should happen next, and you can do anything and then call back into that code basically. But in order for this communication to succeed, they need to agree on the memory layout. So it's really important for this interoperability to document how the memory layout looks. Yeah, and actually like have a sane and predictable memory layouting strategy. Okay. Yeah, I'm happy with this. At some point, if I want to like actually do anything, like enable other people to easily write host systems, I would need to basically write a specification for this memory layout as well. For now, we'll just have some informal specification in comments in our code or something. Okay. So in here, you can see that the Martinaise memory layout is pretty much the same, which is also why I'm pretty confident about that this is going to work out. So yeah, in Martinaise, it's the same thing. We have a maybe of maybe here, and that means that the last byte here determines what kind of memory layout it is. If it's the none variant, then the memory layout of that is just garbage, just padding. Otherwise, otherwise it's the interior thing, so a maybe of string, and there again the last bytes determines the memory layout of the payload. So if that thing is none, then that doesn't have any payload. But if that is something, then that is in this case a string. So a string contains characters, which is a slice of characters, and that contains a data pointer to a char and a length. It just all decomposes into smaller things in the end. Yeah, and like in the end, all memory boils down to some ints. If you look at the two ints or pointers, if you look at the lowest level in here, pointer, int, pointer, int, doesn't even exist, I think. Yeah, int. So really, it's very simple, very naive. Okay. Yeah. Oh yeah, we have one last type, which are lambdas, but I think we'll get to them. We'll decide on a memory layout when we get to that. Yeah. So let's maybe create a memory layout thing. Like decide on memory layouts and then do stuff with that. Hang on, so where's my compiler thing? Oh, yeah, I know. I should open the Plum compiler. And here, rather than this, we'll choose a custom memory layout. So let's maybe create a file, memory layout, memory layout, yeah, okay. Okay, yeah, we will need to have some sort of struct, I guess. Like representation of values. We basically want to replace this, right? Okay. You know what? Let's call this value, maybe just value. Okay, here's an idea. Martinaise, the language I'm programming in, has a thing called opaque types, where you can basically say, hey, I have a type, and this is not a struct. Like, you can't access any fields on this. This is not an enum, which means you can't switch on this. You basically can do nothing with this. But you can also write functions in assembly. So you can say, down here you can say asm, and then in here you can have like, it's not really like production assembly, it's like a bytecode basically. And you can put these bytecode instructions in there. And I think to create an efficient memory layout, we need to have some opaque type. And then we need to have operations on that. Like, depending on the hang on, we need a lower level VM, I think, where the operations are not create a struct or create a tag or push a new object or something, but where the instructions are rather byte based, like based on individual bytes and so on. Okay, so we need to adjust the instruction set of our VM. Sure. Yeah, currently the instruction set is defined in here. Yeah, bytecode instruction. I think we'll actually, let's maybe move that to the VM, because I think it belongs more into here than in the universe. Okay, so bytecode instructions, push object is not really a thing. I think we'd rather have something like push an 8-byte thing, like push 8 maybe, and then byte, and push 64, which is an int. Something like this. Yeah. And then you push something that's already on the stack. And below top, like the bytecode shouldn't work on objects anymore, like the top object and so on. Rather, the bytecode should work on memory, just on memory, which will also make it easier to implement interpreters for such bytecode in other languages, because they don't need to have a representation of objects or like a plum values. They can just say, okay, I have some bytes. That's amazing. Okay, yeah. We have push 8, push 64. We have push 8 from stack. We still need instructions somehow. Yeah, this peaks at the top value a tag. Here the I'll just go through the file from top to bottom. Okay, so code runs in a stack-based virtual machine, something like a mini computer implemented in software. The VM has its own data stack and call stack and operates on instructions called bytecode instructions. From the point of view of the VM, plum types no longer exist. Instead, the instructions operate on memory directly. Reading and writing, reading from and writing to addresses. That's it. Yeah, then we have our VM, which shouldn't really have a universe. It will just use addresses directly, I think. So it will just have a data stack of to-do. Figure that out. And we'll have a call stack of something to do adjust. And then here we have the function ID. Okay. Like I'm just gonna ignore that top part for now and just design a bytecode instruction format that is way lower level than the current one. Okay, so we should be able to push something to the stack, a byte. We also want to be able to push something, an integer to the stack. Yeah, we want to push a byte that was previously on the stack somewhere. We want to push that to the top of the stack. We want to be able to do that. Yeah. And then we want to, contains an offset, sure. We want to do the same for entire ints. We want to be able to pop n below the top. This kind of, kind of difficult to say in general, because what's the top, Is it a byte? Is it an int? Is it something bigger? It's not an object. So I think here we need a tuple, actually. Like what amount of things to, what is the top, basically, and then how much memory below that to pop. Yeah. Pops m bytes below the top n bytes. Nice. And then, should jump and jump table, which should map from string to something. Just says, I think pop top byte. Yeah, pops a byte. Depending on the symbol, jumps to different instruction indices. Yeah, and this is just a list or slice rather of things. Yeah, struct doesn't need to exist anymore because the VM doesn't concern itself with high-level things like creating structs. If you want to create a struct, just calculate the memory layout and then put the fields on the stack, and that's your struct. Same, accessing a member is just accessing, like popping some things, taking the thing that you want to access from the struct and push that on the top of the stack. So I think this we don't need that. Okay, then tags. Yeah, don't really exist. Same with this, same with this. Lambda. Captured variables are kind of, yeah, no, we don't need that. Okay, lambda call. This is an interesting one. Yeah. Yeah. This adds two 64 bits, 4-bit numbers. Pops two 64-bit pins, pushes 4-bit int, pushes the sum as a 64-bit int. Beautiful. Pushes, nah. Adds, then pushes the result. Yeah, okay. Yeah, pops two 64-bit ins, adds them. This one subtracts them. This one multiplies them. This one divides them. This one mods them, I guess. ANDs them, ORs them, and XORs them. Compares them. Okay, and concatenating strings is not something that we support right now. We do support crash, and we should also support memory operations, like allocating memory and loading things, like storing things into memory somewhere, and you know, freeing memory, and yeah. Okay, nice. Like, this is a much lower level sort of VM. And maybe let's group these instructions into like stack operations, I guess. Just to use these, you know, general things like control flow, arithmetic stuff. Yeah, then binary stuff. Hang on, this is arithmetic. Memory stuff, like mallocing something. Ooh. Pops. Size. 64-bit int. And alignment. I think 8-bit is enough. Pushes address 64 bits. Sure. Okay, yeah. Then writing things into memory and loading things from memory. Ooh, I guess maybe the write would be pops address. Oh yeah, we have different, write 8 pops address 64-bit, and what else? And byte writes to that. Writes byte to that address. Wonderful. Then we have the same for 64-bit. Let's call it int. Yeah. And then same for loading things from memory. Right, read and write is what it's... okay, let's call it store. That's more in line with the memory operations, I think. Error. Stuff. All the stuffs. Okay, yeah, this is like much more lower level. I think that's cool. Okay. Dang. No more objects, no more nothing. Like all the magic now disappears once we've implemented that. Cool. Very cool. Yeah, our data stack will just be a list of bytes. Cool. Cool. Our call stack entry. What even, like... The question is, where do bytecode instructions exist? Like, does the VM keep them around? I don't actually think so. I think they are just, somewhere in memory. So this really is just an address. Damn. Which means that we don't have this, or this, like any of this, actually. It's just that. Yeah. Points to slice of, not even a slice necessarily, just bytecode instruction. Instructions plural, because we assume that at that address in memory there were just bytecode instructions chilling there next to each other. And yeah, when we executed an instruction, we'll just move to the next instruction. Yeah. And when we call something, yeah, we actually just call. Yeah, we don't call a fun ID, we just call an address, I guess. That seems... How does bytecode look in memory? Set the instructions operate in memory directly, reading from and writing to addresses. Okay. The idea is that instructions live somewhere in memory. Data set call stack. It also needs, when you run the VM, here, call stack at maybe top. Oh, it always gets the, okay, the top of the call stack is basically the current instruction, which makes sense, I think. Yeah. Okay, the idea is that instructions and objects live somewhere in memory. We don't need to know their types. LLVM just operates on raw addresses. And then I get a completely different object 1 is object 2. Here you have some instructions maybe. Or just floating around in memory. Instructions and objects live somewhere in memory. We don't need to keep track of them. For example, by putting them in a list. They just float around. Just like our own data structures. The VM just operates on their raw addresses. Okay. Yeah. That seems kind of crazy, but it's also pretty cool. They're just memory. Figure 1. Objects floating around in memory. Beautiful. Cool. Yeah. So we have kind of a, not specification, but a definition of a low-level VM. A lower level VM than previously. And yeah, hang on, so we have the data stack, which are just bytes. And instead of writing some objects or something, we would just write bytes in here, I think. So this is not some ID, no, this is just a byte. And then the call stack is, right, for each call, and that's just an address, yeah. I guess we'll just write addresses in there. Okay. Simple. Then, when you call new on a VM, oh yeah, to create a new object here. No, that's not a thing anymore. You can get an object from a VM. Nope, objects are just addresses and you can get them directly. You don't need to, yeah, I think pushing and popping does make sense, some sense, you know, push. Yeah. I'm just going to remove them for now. I comment them out. Yeah. And call is the main thing, right? So call just takes, I guess, a main fun, which will just be an address later on, and arguments, which will be a slice of addresses, maybe. Okay, returns an address. I think so. Yeah. Okay, so we create a VM, nice, with an empty data stack and an empty call stack. Beautiful. And then the arguments. Okay, they don't really. Do we need arguments? I don't think. I think we'll just have things that should be on the stack, like a slice of bytes. So it's rather like an initial stack is a slice of byte, and the data stack is the initial stack. Yeah. To list, I guess. Okay. Yeah. Then we don't have this. Yeah, but on the call stack we just push an entry, which will be the function address, because functions will just have addresses. Okay, and then we have on current call. Yeah, we need some sort of return instruction or something. Because we can't check if we are at the end of instructions, because instructions are just somewhere in memory, so we'll just read memory afterwards. Like the memory doesn't tell us that some data structure just ended. Yeah, returns from, just calls another function. I'm not sure about that one. No, returns from a function call. Okay, yeah. Okay. I like this kind of low-level stuff, to be honest. This is pretty cool. So we say get maybe ref of the last one. Ah yeah, if there was nothing on the stack, then we're done. Yeah, that's true. And then we get the we get the instruction, which will not be some weird, we look in the slice and get maybe an unwrap, and no. We just dereference an address basically. So this would be current call dot instructions, nope, dot instruction. Yeah, current call dot yeah, and then there's this to reference thing in Martinaise, which turns an address into a reference of the type you specify. So we know that this points to a bytecode instruction. And then we dereference that reference to get the actual instruction. And yeah, this doesn't exist, because instead we'll have a return instruction. Okay. Yeah, then the current call would just be plus, like this, current call is current call plus stride size of bytecode instruction, which will just make this address point to the next bytecode instruction. Yeah. I mean, yeah, we could even just turn this into a pointer of bytecode instruction. But then it looks like there's just a single instruction in there, so I'm just gonna keep it like that for now. Okay, yeah, then we can switch on that instruction, and we need to handle all of this. And yeah, most of that will probably be pretty similar, but I'm just gonna copy that here and remove the comments. Yeah, basically all of them. Cool. Okay. Nice. So, when we want to push a byte, we'll actually just push a byte to the data stack of the VM. So vm.datastack.push byte. When we push, let's call it a word, then, we want to push a word to this, which means 8 bytes, which means converting an int to bytes, that should work somehow. I think we'll just do something. Yeah, we'll just cast this in a weird way and then figure this stuff. That should work. Let me maybe take the word. That's an int. 64 thingy. Take a reference to that. And then convert that to an address. Okay. And then convert that to a reference of bytes. So now we have a pointer, and byte is basically our type. Yeah, and we'll create a slice from that. And the slice has data and a length. Yeah, so now we have a slice of bytes. Nice. And now we push those bytes. So for byte and word bytes, do vm.datastack.push that byte. Cool. Then we have push from stack, which would have to read something from the stack first. So vm.datastack.get length minus offset. I think it would have to be like this, because 0 means get the first byte, yeah, which is the length minus 1. And then 1 means get the second byte, and so on. Okay, so this is the byte, and then we say datastack dot push the byte. Yeah, basically same thing here. I think we'll just start a bit earlier. So datastack then minus 1 minus offset. Oh, I see, because here we get 1 byte, here we get 8 bytes. So if offset is 0, we want to get the the top 8 bytes and push them again. If it's 1, then we want to skip the first byte and then take the 8 bytes after that and push them to the stack and so on. Yeah, so then for I in 0 to 8, we basically say, hey, data stack, we want to push data stack get of start plus I. Yeah. Okay, then pop n below. Yeah, it has a tuple. That contains, what was it, first n and then the number of skipped ones? No, first the number to skip would make sense. Yeah, below the top n. Oh, so it's not pop. Top below top, I'm gonna call it. Amount. Pops amount bytes below the top. Yeah, I guess. For skip. Below the top skip bytes. So we have skip and amount. Skip and amount, and then basically we remove, oh, you can remove a range from a list, I think. So you can do the data stack dot remove. I hope I implemented that. Yeah, basically create a range from the data stack len minus skip minus amount, and the range should have the amount, should have the length of amount. Yeah, dot dot plus, creates a range that starts here and has that length. Okay, that should work. Then we have a jump, yeah, but it just jumps to an address, which is amazing. Hang on, jump int. Oh, inside that. Ooh. Does this make sense? Nah. Jump address. Yeah. I think this will just be addresses. And the lambda call will... I'm not sure how lambdas are exactly represented, so let's just put nothing in there. Then I know that I still need to do something about that. Yeah, I'm not even sure if we need a separate instruction for that, or if lambda calls cannot be represented as normal calls. Maybe. Okay. So we have jump to an address, which would just be jump address to the given instruction index, no, to the given I mean, this is pretty obvious. Jump address VM dot, does it just the VM down here? Hang on. No, current call. Okay, yeah. Jump table. Pops a byte. So vm.datastack dot pop. And then depending on the byte, we jump to a different instruction. So table.get byte, and that is the current, we call that. Oh, we jump there. So current call is table get byte. Okay, yeah, lambda call to do. Yeah, just calling some address. Basically means this, pushing something to the call stack, indeed. The new function we want to call, that makes sense. Yeah. Okay. Yeah, I guess vm.callstack.push target. Simple. vm.callstack.pop. Nice. Then, yeah, adding two numbers. Yeah, would be something very similar to this, by the way. Not really. This is like pushing a byte. Yeah, but I need helper functions for that. So yeah, I'm gonna call it push int, maybe. And you just give it an int, and then it gets the bytes and pushes those. Beautiful. And similarly pop int pops an entire okay, we need something very similar to this actually. We take the data stack, vm.datastack to slice.subslice of the last 8. We want to get the last 8 bytes. Yeah. Okay, we don't need this. We can just say get. We want to get reference to the eighth last byte on the stack. We convert that reference to an address, and we'll just interpret that as pointing to an integer, which we then dereference to convert those into a 64-bit value. Beautiful. And then we need to pop 8 values like this. vm.datastack.pop, and finally we return the value. You can zoom in a bit. Okay, so then this, some of this gets easier. Yeah, push, this word would just be vm.push int. Yeah. adding two numbers just pops two numbers. So pop int. Oh, hang on, no, just the end of pop. And then we have yeah, that. Ooh, you know what? Let's do it like this. Is that the same? Yeah, because unlike C, by the way, the arguments to function calls, like the call to the plus function, they are guaranteed to be evaluated in the order that they are written here. So we can just do that, which I think makes this like parallel structure between these cases really clear. Yeah, we can divide them, we can calculate the mod, we can comparing them. I'm not sure. We don't need that. We could just subtract them and that's it. Yeah. Yeah. Don't need that. That's crazy. Yeah, I think like we do we need anything like? No, not really. Not really. I'm just gonna remove this. If we need that at some point, we can still add that. Okay, ending integers, ORing integers, which I think just works like that. XORing them, which is this, hopefully. Oh, malloc is interesting. Amount is vm.pop int, and then we have the alignment. This is vm.datastack.pop, pops byte. And then we actually call malloc with the size, that's what it's usually called, and the alignment. And that returns a new address, which we then push. Yeah, exactly this. Then we push int, the address cast to an int. Yeah, cast from address to int. Okay, beautiful. Well, beautiful is, and it's not beautiful, but it works. So storing bytes. Yeah, basically we pop something like an int. Pop int and cast that into an address. And then we interpret that address as a reference to a byte. So address.toReference to a byte, and we set that to vm.datastack.pop, to the byte that we pop off. Yeah. Storing something like an int in memory is something very similar. It's just pop int. Beautiful. Then loading something. yeah, will also be similar. We take the address and the byte, and the byte will be this. Yeah, I mean, let's just say vm dot data stack dot push that. And we have vm dot data stack, no, just vm dot push int of the address that we have to pop before. This is so low level. It's amazing. I'm very aware that we'll probably we will break the language doing this right now. But it will be fun. Yeah, that is kind of interesting. So crashing needs a string, and string consists of an address, popping an int, converting that to an address, yeah, and a length, which will just be popping another int. That makes sense. Yeah. Okay, and then we address and len. Then we have the message. Which will just be a string. We'll create a string from scratch. I think a string has data and len, so we could just say data equals. We could just call this data. And now we have a string. I think that should work. Yeah, this is not true because this entire thing results in a data stack, so in a slice of bytes. Which is kind of, you call something with an initial stack, a slice of bytes, and it results in some other bytes. Damn, that is a bit more low level than I thought. Which means that it will take some time to bridge this abstraction from our relatively high level representation of source code into something like this, into these instructions. But I do think it's kind of cool. Yeah, for this, the individual calls are also not really, there's not a lot happening there, so I think we can display them on the same line. And yeah, without even importing this, let me just maybe comment that out and just create a VM manually. So I think we'll need something like we'll have an uninitialized slice of bytes, perhaps. I have bytecode instructions. And yeah, length, I don't know, let's say 20. Yeah, and then we'll just set the instructions here. So we could just, let's just build a list and then, so bytecode dot push bytecode instruction dot push 64. We want to push a 2, we want to push a 3, we want to add them. And we want to return. Don't forget the return. Yeah. And now we should be able to call this thing, I mean, let's be honest, this is really just an address. Oh yeah. Damn. Yeah, call address. Okay, so bytecode is a list. And the list has, what is it, data? Something? I'm not sure. We're gonna convert that to an, no, hang on, it already is an address, isn't it? List. Let me maybe open the list from the standard library. List. Yeah, the list has data, which is a slice. And hang on, the slice was in mem. Yeah, the slice also has data, which then is an address. Sure. And we don't have any bytes to put in here. Yeah, so the universe things are kind of broken right now. Okay. Yeah, address plus doesn't exist. Oh, it's an AND address. That also seems weird. Hang on. What do we do here? We take get maybe ref. So this is actually a reference to the address. That then points to the actual data structure. So this would first have to be dereferenced. I think instruction is something that does work. Yeah, I think we'll need to do it like this maybe. Get maybe ref. Yeah, this is like a reference into the call stack actually. And then from that call stack thing, I mean, what's really on the call stack are references to bytecode instructions. So we get the underlying bytecode, like pointer to the bytecode instruction. Now I think we can just do this. This takes the current call, again, a reference into the call stack. Dereferences that to get the concrete address, which is a reference to a bytecode instruction, and then it goes there to memory and then fetches that instruction. And here we basically override the thing in our call stack with the existing address that's in there. Yeah, that makes sense. Plus the stride. Yeah. I think if we have a reference, we can also do this. Nice. Yeah, pop n below top doesn't exist. N below top. Oh yeah, it's just pop below top. You don't handle compare 64. Oh no. Yeah, you don't. Oh, hang on. I wanted to remove that. Yeah. Mm-hmm. 98 or 99 nowadays. Push int. Oh. Yeah, I think that's a common. Oh. Yeah, VM push int should always be LLVM.end.push int. Okay, and then inside of push int, the word is not known. Yeah, I know. Yeah, let's maybe call this int bytes as well. Okay, try to assign and byte. Yeah. True field data of type address. Oh, nice. So this is a slice of byte, but really it just contains an address. Yeah, that makes sense. Oh yeah, so we need type annotations here. Let's check. We do need them, right? Yeah, type variable t is unbound. So this is a slice of bytes. Beautiful. 112 is down here. Somewhere here. Yeah, current call equals address. Oh yeah, because this is the pointer into the table. Into the call stack. Yeah. And we want to adjust that for jumps. Yeah. This is the signature get slice address byte. Oh yeah, from a slice, jump table, we actually want to get the byte converted to an int. I'm fine with that. Okay, so we have return. Previous cases do nothing. True, and we just ignore what we, the thing we popped. Yeah. Or, okay, so there is or as a function, which, oh yeah, which makes sense, because this is not like short-circuiting in any way. Yeah. Yeah, malloc needs 2 ints. The alignment, let's convert that to an int. Okay, so popping an int from this list. Yeah, that's data stack. Nope, just under pop int. Then 14243. Ah yeah, here. Invalid assign needs a byte. Values int. Store 64. Oh yeah, we need this. We treat that as a reference to an int. This call doesn't work. Push int. Makes sense because we treat this as reference to an int. Okay. Yeah, somewhere where we need to turn this. Hang on, it is a slice. Expected slice. Oh yeah, the return value. Makes sense. Not the argument. So the return value, you can convert that to a slice of bytes. Okay, yeah, I guess that's working. Nice. result. And then maybe let's print the individual bytes. And that new line.
Yeah.
And if you're wondering why is it like 5 and then 0 as well, these are the bytes that represent the integer int. And the integer 5. So yeah, bytes really are not, yeah. We should think about two things. We should first think about little endian versus big endian. So if you save an 8-byte integer, how are those bytes arranged? And the way that Martinaise does it, and that most CPUs work, and which is also the way I think we should do this, is storing this in little endian, which means that the least significant byte is stored first. Which means rather than having this in a human readable form, you know, the 5 here at the end, we have the 5 here in the beginning. Which is, you know, it's not like a big decision or something, it's just you need to decide on something. And the second thing I was thinking about is, oh yeah, does the stack grow to the top or to the bottom? This is an interesting one. Because currently it grows to the top. And that seems reasonable. Especially if you consider that this VM should be easy to implement in other languages. You know, that you should, like, having this bytecode, you should be able to embed Plum programs in other programs by just writing a very simple bytecode interpreter, and then everything works on top of that. I do think though that it is kind of some machines include instructions that assume a stack that goes to the bottom. Like this is how it's done on x86, that the stack grows to the bottom. So the push instruction, for example, it decrements the stack pointer. So we have a pointer that points somewhere in memory, and by the way, stack memory is not anything specific. It's just the same memory. We just call some region the stack, and use that for all of the local variables. And that is what makes the stack so efficient. That all of the function calls, all of the temporary variables that you use, they are all in the same memory region. So the memory accesses there are very localized and very cache friendly in that way. Right. So anyways, we have the stack pointer that points somewhere in memory, and we decrement the stack pointer to make space for the new operand we want to push there, which means the stack grows to the bottom. And it is pretty cool that x86 that we have instructions that do that automatically. Like later on when we want to compile the bytecode to machine code, maybe it will be more efficient to have a stack that grows to the bottom than to the top, because for a stack that grows to the bottom we can easily just use the native push and pop instructions to manipulate that data stack. But then the question is, if you push hang on, I think we can make the bytecode agnostic to the stack direction. Like, even if you have a struct containing x and y, yeah, if you want to load that from memory and work with the values, you would basically push that on the stack. But you would do that in a field by field way. You know, you would first get the x from memory and then get the y from memory, for example. And then you know which order they are on the stack. Yeah, it's just when you also the endianness is kind of it doesn't really matter, you know, as long as you don't push a 5 or a 2 or something and then you pop individual bytes, it's totally fine. Okay, so I think, yeah, that's pretty cool. Let's leave the endianness and the stack direction undefined. The endianness of ints and the stack direction are undefined. Implementations of this bytecode are free to choose whatever they want. In particular, this means that bytecode should not depend on these things. Yeah. For example, you should not push 64.5 and then use pop 8 to pop individual bytes. Beautiful. Really, really beautiful. Okay, yeah, which means I think we do need special, we maybe need special instructions for converting, for getting the, the individual bytes from a 64-bit integer. Basically have an extra instruction, get least significant bit, get to get the lowest bit from that, or converting a byte to an int. But yeah, I think that's totally fine. That's reasonable. Okay. So the only way that we realize that this thing is by looking at the individual bytes outside of the VM. You know, the bytecode will never see this. And in fact, we know that this thing returns an int. So we should be able to say result is a slice of bytes. We should be able to say we take that slice of bytes, take the data, which is just an address, convert that to a reference, to an int, and then dereference that. And then we should just get 5 as a result. Never mind. Oh yeah, now this doesn't work. This will just be, you know what, I'm just gonna leave that here, but comment that out. Result. Yeah. Okay, yeah. So we can write code that returns an integer. Cool. You know what, I'm gonna take a break and eat something because I think there's a natural resting point for now. You know, we have implemented a nice low-level VM, which incidentally is also the initial vision of LLVM, which stands for low-level VM, which stood for low-level VM. Now it doesn't. Now it just stands for something. I think for nothing actually. Yeah, but we've implemented a low-level VM that is entirely stack-based, that works apparently. I think we still need to test some things like memory allocation, loading, writing, and so on. Yeah, but I'll do that after the break. Yeah, so see you then. All right. Yeah, let's first write some other programs just to test the other instructions. Yeah. I think it also makes sense to print the intermediate stacks so we can better understand what the VM is doing. I think there should probably be some sort of printing what instruction we have, but also printing the stack, shouldn't there? If not, then let's maybe add that. Yeah, something like this. Sure. So we loop and we say, hey, this is the stack. Yeah. Yeah, new lines would also be nice. Yeah, plus let's maybe also print the instruction, because why not? Nice. Okay, so we have an empty data stack. We see push the number 2 as a 64-bit integer, so 8 bytes. We have the 2. Then the 3, then add, pops the top 2 things from the stack and pushes a 5. And finally return and we exit. Beautiful. Yeah, so let's maybe, hang on, what kind of instructions do we have? I think it would make sense to, I think it makes sense to have some tests for that actually. Maybe. Or I'm just going to, let's not do that. But I do want to test this one, like push 8 from stack and just see what happens. So what if after this we also have push 8 from stack, and then we can say please push the 3 again. This should be this byte, hopefully. Okay, nice. Yeah, that works. Beautiful. Oh yeah, now the the add instruction works on these values. Also makes sense. How about this? Yeah. So because we only push 7 things, it interprets this as a number. Hang on. Nope, this. Yeah. And then this. Yeah. Oh, yeah, okay. So here we push that part to the stack. Also seems correct. Pop below top. That's pretty cool. Yeah, I want to pop 7 below the top 2. Now we can't really test that, can we? Nope. I think I can use numbers with radixes. Oh, but like this. I think that works. Okay, yeah. Yeah, pop below top means we keep the top 2, and yeah, then we pop 7 below. So 1, 2, 3, 4, 5, 6, 7. Yes, that's exactly what we did. Beautiful. Yeah. Let me check on the camera. Camera is working again. So, pop below top works. Jumps are kind of insane, actually. So, let's maybe introduce a jump here. Yeah. So because jumps go to absolute addresses and jump to some address, we basically need to make sure that when we push other instructions, we don't reallocate things here. So actually this should be a slice, oh, hang on, an uninitialized slice of enough instructions. And then we set the instructions instead of pushing things. So we do get ref, which returns, you know, like a pointer to the corresponding slot. And yeah, we just do things like this. And here we should be able to do something to, for example, just directly jump to that instruction. And the reference converted to an address. Yeah. So this should skip this instruction. Oh no. Okay. What's going on here? The data. Oh yeah, because we already have a slice, it's easier now. That's okay, the result might actually be correct. Hang on. Yeah, hang on. Before it was okay, so 17, and then all the 34 and 51. And now it's only 17 and 51, and the 34, which this was apparently, is no longer there. Damn. Okay, so we can just jump to arbitrary addresses, and at those addresses should be bytecode instructions. That seems unsafe, and it is, but it works, so. Oh shit. Okay, wait, hang on. We get a reference into that slice, into the third instruction, get the address of that. Yeah. I mean, it makes sense. It makes sense. Okay, so jump apparently works. Jump table, sure, I'm not gonna test that. Lambda call. I'm not sure what to do about that. Oh yeah, calls and returns. Could we say, I don't know, call? Probably, right? This will be interesting. Okay, so we push, the 17. Okay, then we call that instruction. Sure. And then we basically skipped again, the 34 instruction, which means we're basically at this instruction here, pushed those things, then we push 8. Oh no, that does not seem correct. That does not seem correct at all. I'm running call. There it says push, but that looks correct here. This looks fine. By the way, also I'm just gonna print the stack as hexadecimal, so things are a bit easier to read. Yeah, byte. I think it was radix 16. Okay, so we push the 1s, and yeah, let's maybe add 3 more 1s, just so they use the entire 8 bytes. Beautiful. Okay, so we have the 1. Okay, then we push, oh yeah, we call something. We push the 3, correct. Now on why push 8? Where does that come from? Let's try to work through this. So we have the current call. We get the instruction, which is apparently correct. And then we set the current call to the next instruction. Should work. Yeah, this should work. Okay, when calling something, we just push the target to the call stack. So the next time when we want to execute an instruction, we actually just use the new instruction. That looks correct. That doesn't make any sense. Push 8. Okay, you know what, let's just go with that and then we'll see what goes on. So then we have the add instruction, which again, this is completely correct. Which then, okay, it adds the wrong things, I get that. And then we return from the function call. Which means that now we execute the previous instruction. Hang on, we pushed this, we pushed this, which apparently was interpreted as a push 8. Oh no. 1, 2, 3. Well. Well. There was just, uninitialized slice means there's just some garbage in there. And yeah. Okay, this looks correct. So we push something here, we add those, and we return. Boom. Which means now the call is done, and now we're here again. So now we push the 2 and the 3, and we add those to get a 5. Beautiful. So call and return work. Right. Okay, so I'm pretty confident in these instructions. Yeah, adding, I mean, yeah, they are implemented here. Adding works. The others are like there's nothing wrong with this, you know. Okay, and also with this, like that's fine. Yeah, the only remaining thing is basically memory and crashing. Ooh, that's gonna be fun. Some memory instructions. I basically want to see. Okay, so we want a 64-bit thing that tells us how much memory we want to allocate. So let's say 20. 20 bytes. Yeah, it's in bytes. And then the alignment, which will be a U8, right? Pops size and alignment first. Okay, so you know what? Let's switch this around. Let's say the pops alignment and size. Yeah, because later on I want later on I want to have some sort of calling convention that if you call a function, that the stack has to be aligned to 8 bytes. And that means that all of the reads and writes of 64-bit numbers from and to the stack, they are efficient as well. Yeah, and for the malloc, I think it makes sense to first have the, to have an aligned size on the stack, and then on top of that, the alignment, which is then popped first. Okay, so first, like this. First, how much memory do we want to allocate? And then what's the alignment one? And then down here, in the case malloc, we need to switch that around as well. Oh yeah, that was, oh yeah, no, that's correct. Okay, so we have this, then instruction malloc, which will pop those and push an address instead. And then we just add some random number to that address, because why not? Okay, oh, it's a byte, push 8. Oh, I see. Lower byte to convert this int to a byte. Crazy, crazy. Okay, so let's see. Initially we have 14, which is the hexadecimal representation of 20, and the alignment is 1. Then we run the malloc instruction, which will pop the alignment and the amount that we want to allocate. It allocates memory for us and pushes the address of that onto the stack. Pretty nice. And you know what, let's always print like 2 characters so things are aligned. Somewhere here printing, yeah, radix. Dot pad left, I think. And we can pass in a string, char, I think a char. Char 0. Expect a closing parenthesis of call. How a char? Oh, I think, yeah, this was a char, right? Yeah. Okay, so if pad left, oh yeah, true. So we have a string, and we also need the amount that we want to pad to. So we want to pad to 2 characters, with the 0 as the char, as the padding char. No, not quite. We want to interpolate this. Nested string interpolations. Beautiful. Yeah, okay. Yeah. This looks cool. I mean, this is crazy. And then we just we push the address. So this is some memory address. And then we push this thing, and then we add that to the address. Nice. Well, this actually moves something there. Hang on. So there should be load and store instructions. Yeah, 8 and 64 bit. Okay, so we allocated memory. I think next would be to not add something, but instead say, hey, I want to store that. Pops an address and an int. Okay, so the int should come first. Yeah, let's just move that up there and adjust these. So we push an int. We allocate memory for that, and then we store that int in memory. So now the stack should be, oh, it should be empty, right? Let's maybe, okay, let's switch this around again. Yeah, let's say we allocate memory. Oh yeah, but now we push 64 from stack 0. So the address that is on the stack, we basically duplicate that. So now it's on the stack 2 times. Hang on, the other way around. We first put an integer there, then we put the address there, and then we call store. Okay, so now this number should be stored in some address in memory. That is crazy. Oh no. Yeah, I mean, true. So apparently Martinaise is an unsafe language, which it definitely is. Okay, interesting. Yeah, let's maybe add some debug prints to that. Hang on. Let's maybe first double check the store. It pops an address. Let's change this, because again, with a byte, the address shouldn't be above the byte. So let's say pops byte 8-bit, pops address 64-bit, stores byte to that address, and I'm going to replace the end with this to make sure that it's clear that these happen after one another. Oh no. Pops something, pops the address. Yeah. Beautiful. I wouldn't call it beautiful, but okay, so we duplicate the address. We can still do this. Oh, I see. We overwrote some instructions. Yeah, now we also need to fix the implementations down here. Yeah, so first pop the byte. And here first put the int. Okay. Yeah, load. What is it saying up here? Yeah, that doesn't make any sense. We want to load something, so it should just pop the address. Loads byte. I think this is just pure copy paste. Pushes that int or byte. So it pops an address, loads byte from that address, pushes that byte, and for ints it just loads. Okay, yeah. So these are actually unaffected. Makes sense. I still see a segmentation fault. Oh, now I don't. Okay. we allocate memory using the malloc bytecode instruction. Crazy concept. Yeah, we duplicate that address on the stack. So now it's here 2 times. And we push some payload we want to save there. We run store, which consumes these 2 things. And now, hopefully in that memory, there should be something stored. So yeah, right now we say the result is an int. But yeah, we know that this is just an address. Oh, yeah, so now we're just going to print the address, which, true, it is this address. Encoded in little endian again, so that they're not intuitive form for humans. So first we have the 0e and then the 8, and then the last the 8. Okay, but now we want to load something from that address. So we know that that address is a reference to an int. We dereference that to get the actual integer, and then we print that with the radix 16. Should print a lot of 3s now. Okay, we wrote something into memory. That's how it goes. Ah, oh, that's so cool. Okay, so we stored something. Yeah, let's try to load. Just load. The address, we copied that up here, so it should already be on the stack. Yeah. And now, oh yeah, now the thing will segfault in the end. Yeah. Oh, it was earlier than I expected. Hang on. Load. What do? We push something from the stack. We put copy pasta. Yeah, copy pasta, of course. Yeah, like this is not an intuitive way to encode instructions, by the way. Just in case you haven't noticed, Yeah, this is what I expected. So we store something. We store the 3s in memory, running store, boom. Nothing on the stack here. But then we load them again, which means we consume this address and instead push the value that is in memory there. Okay, and the same thing should work for bytes. So you're pushing bytes, storing that byte, and then loading that byte. Let's say the 7, like 42, which should be 2A in hexadecimal. Beautiful, beautiful. Yeah, we put the 2A here, we store that in memory, and then we load a byte from that address. Boom. Okay, and 2A is apparently also a valid address, and at that address is something else. Oh, amazing. Amazing. That's crazy. Okay, let's try something else. Let's say we want to panic with a string. With what string? Well, with this string. Hello. Hello, panic. And what we're going to do is we're going to push the pointer of that string past to an int. Then the length of that string, and then we're going to run the crash instruction and see what happens. Oh, shit. I mean, this is definitely printing a string, yeah. Yeah, it's not really a good string, but yeah, okay, so the way Martinaise works is that all of the strings all of the string literals in your program, they're moved somewhere in memory, so that your actual string types, they can contain a pointer to that memory and then a length. And that means that somewhere in the memory there are like all the string constants, and apparently we print that. Oh, and I think I know why. Probably this is just the wrong order. Yeah, let's maybe switch that around and see if this works. Nice. Yeah, running crash, and then VM crashed, hello panic. That's amazing. Great. Okay. Yeah, so all of the instructions seem to work correctly. to be honest, like, I have written bytecode VMs before, but nothing this. Okay, I have written low-level VMs before, that also like read from memory and stuff like that, but not a stack-based VM that also has like malloc as an instruction. And I think that's like that's pretty cool, just saying malloc and then boom, you get an address on the stack. That's crazy. Okay. Yeah. I should probably commit this. Yeah, let's open GitHub desktop. Let's see. Lots of fluff. Oh, yeah, wrong repo. No. Yeah, we don't use that yet. Yeah, I'm gonna push this just because that's something that works at least. Yeah, not sure about that. Add VM. Or like make VM low level. Like low level. What? Yeah, let's make it low level. Crazy. Okay. I guess next would be compiling code to that instruction set. This is so low level, we can basically, we can translate most of these instructions to assembly instructions later on. Or like to machine code and then run that directly. But for now, yeah, the question remains, how do we get to this? So let's maybe look at what we had previously. We had the yogurt before, which is a compiler stage that basically contains types, and we also printed that here. Yeah, here. Whew. So the question is, how do we map these instructions? How do we map these expressions, I guess, into instructions? Yeah, without optimizing too much of that, let's just go one by one. So you have, I don't know, you call some function, and then you just look at the first instruction, and this would push a 5 to the stack, a U64, like 8 bytes. And then what a call instruction does is it actually lowers to a call, I guess, but before it also pushes all of the arguments. That's actually like pretty similar to what we do currently, except that now we need to yeah, we need to make sure that we basically need to have memory layouts or something like that. we don't yet. We don't yet. Let's just look at this. Yeah, we don't really have. I don't just want to remove all of that because it is. We do need this somehow, you know. Just not quite like that. So let's maybe re-import that and now let's first think about memory layouts and then we can. Okay, so memory layouts. And also import memory layouts here. Layout thing. Not sure. Layout. Even simpler. Memory layout. I think we basically want to generate some memory layout. And memory layouts, they contain a size, I guess, and alignment. And then depending on the type that they stem from, they should have different information. So, okay, so maybe add a kind, like memory layout kind, and an enum memory layout kind, kind of an extra information about this layout, apart from its size and alignment. So there should be some way of saying this is opaque memory, which basically says as well, this is like a fundamental primitive type. Call it primitive. Yeah, primitive is nice. You know, and an int is just size 8, alignment 8, kind primitive. So a string is size 16, I guess. You know, pointed to the actual string content and then length. Right, so size 16, alignment 8, kind primitive. Nice. Struct would have, you know, well, struct is different. For struct, the size actually differs. The alignment can differ. And, okay, currently it can't because I think the alignment is always 8, but in theory. And the kind should have extra information about the struct. Like, for example, where are the fields inside of this memory batch, you know? Yeah, so let's maybe have, oh yeah, where are the fields? And also the memory layout of those fields, maybe? But maybe not really, because I'm not sure. For now, let's just have a map from this field name to the offset. Field names to offsets. Like at which position in the struct is the field. Yeah, and yeah, there are tags, aka enums. Yeah, it makes sense that the value was a tag, but the type is enum, and memory layouts always refer to types. So I think an enum should have the payloads in memory, and depending on the payload, that's like a different encoding, and then 1 byte for the tag afterwards. And yeah, we will add some special casing later on, maybe for enums with like lots and lots of variants. We may need 2 bytes or 3 bytes. I don't know. Yeah, some number of bytes. And also, if the enum doesn't have any variants, that we don't need to store anything. Or it only has 1 variant, then we also don't need to store a tag. Okay, so an enum has basically a map from string. No, it has nothing in there. Actually, let's say it has the size of. No, it has nothing in there. Nothing. Yeah. Sure, it has some payloads, but they have some other memory layouts, but it's not like we need to arrange them in the enum somehow. Oh yeah, lambda will also just be a primitive thing, and code as well. Okay, so we have these, which, yeah, cool. Calculating memory layouts. That is nice. So, let's add a function, memory layout, where we can pass in a yogurt, a breakfast, a plum type. Yeah, then depending on the type, we do different things. So we have type, which is a plum type, and it returns memory layout. Yeah, so far so reasonable. Then we switch on the type. And we need to handle all the possible types. If it's a primitive type, then it's kind of weird that it's based on the name, but yeah, I don't know. So primitive types will have, well, if the name is int, then we will just return, like, have a memory layout where the size is 8, the alignment is 8, and the kind is memory layout kind of primitive. Yeah, then there are also strings, which will be pretty similar, except the size is 16. And otherwise, let's just add it to do. Handle primitive type and routing primitive type. Yeah. Beautiful. The never type doesn't have any. Oh yeah, it does have a memory layout of size 0 because it never needs to be stored. So we never need to has no information. Okay, yeah. Beautiful. Yeah, next, struct. And I think this is the most complicated one. So we're gonna leave that for later. Yeah, for an enum, basically we memory layout all of the variants. Basically we have a candidate size, which is like a candidate payload size, payload alignment. 1 is the minimum alignment. Basically we don't care which byte we have. Like every address is divisible by 1. Dividing by 0 is bad. So for each variant in the enum, we basically memory layout that. We have multiple enum payloads, and we do want to layout them in very in a smart way, Yeah, so I think we actually have something very similar. We'll have a list where each variant tells us the offsets of the payloads. So again, from variant to variance to payload offsets. Yeah, this is gonna for each of these enum payloads, it's gonna contain the offset in the entire thing. Okay, and to do that, I think we can just basically create a plum type struct for that, because we want to lay them out in the same efficient way as the struct. Yeah. But then we need a map from, okay, let's maybe layout efficiently is something we'll have, where we basically get types, and it returns types plural, like this, and it tells us something like this. Yeah. Okay, so the idea is that in here you can say variant value, which is the slice of plum types. You can lay them out efficiently. Yeah, you know what? Let's make memory layouts like deeply descriptive, which means that in here we don't just save the offsets, but also the layouts of the fields. Yeah, no, that's struct memory layout contains offsets. No explanatory comments needed. That's useful. So you have the offsets of the fields in the global memory layout, and then you also have the layouts of them, which will be a map from string to memory layout. We could also have a map from the name to a tuple containing the offset and the layout. Yeah. Yeah, okay. Something like this. Oh, hang on. Yeah, for this is gonna be pretty similar, I think. Except this will just be a slice of this. So maybe this is the part we need to factor out. So an offset and layout contains an offset and a memory layout. Nice. And then this just points to, maps each field name to offset and layout. Yeah. And same here, except for the variants. And each variant kind of has a slice of payloads. Pretty nice. Pretty nice. Okay. Then in here we have memory layout as, what's going on here? Strange. Yeah, memory layout in a type results in a memory layout. Yes, that makes sense. Yeah. And then here we switch on the type. If this is a primitive type, we do stuff. Okay. Yeah, never, then we have struct. And oh yeah, this down here. Oh yeah, I can take a slice of plumb types and can return a slice of offset and layout. Ooh, I like that. Shouldn't it also contain like the total size and alignment and nah, that's fine. Probably. Yeah. Okay. So yeah, this is to do. In here we call layout efficiently on the enum variant variant payloads, yeah, giving us a layout for all of the fields, and then we need to say the payload size, needs to be the maximum of the current payload size and this new layout size. So layout, basically all of these together, the sum of their sizes. Same with the alignment. By the way, same here for the fields. Okay, this is kind of similar. I like that. Ooh. Maybe. Should we maybe have a slice of this as some special type? I feel like this is an abstraction that spans two layers. You have the abstraction at the bottom that basically tells us it's basically like a description of the memory. Like there were multiple fields next to each other. There are multiple fields that overlap. There are primitive fields. And then the mapping between actual types and their field names and variant names and so on to these lower level layouts is another layer. And currently the memory layout contains both of them. It contains a map from the actual value, like strings and so on, to these layouts. Maybe it makes sense to separate that out. Yeah, I like that. So we only have two kinds of memory layout. This is basically a slice, and this is also a slice. Yeah, and there's not like a struct. So each memory layout thing can either be like completely overlapping, you know, or it can be let's say this is the AND thing and this is the OR thing, maybe. Like this is either one of these memory layouts. This is a combination of these layouts at different offsets and layouts, and they are not overlapping. So the disjunct and disjunctive. Yeah, I'm not sure. Not sure. Okay, but we have something. I think this is a better abstraction. You know, it doesn't concern itself with the mapping from yogurt types or user level types to memory layouts. This is just a description of the memory layout. And sure, you will have to do stuff like this, like 0.0.1 or something, to get the actual fields, or the OR thing will also be, like, for example, an enum will map to an AND of the payload and another memory layout, which will then be the tag, I think. Does that make sense? But then again, it's only ever used for that. I don't want to make something like overgeneralize stuff, you know. No, okay. This is gonna be a map from string to offset like that. Sure. And enums are gonna be a map from string to a memory layout. Okay, that actually makes sense. And this inner memory layout does not contain the tag, only the layout of the payload. And it contains payload layouts, I don't know. Yeah, something like this. Okay. Yeah, that makes sense. Okay, so for a struct, let's say we get all the fields. Which will be field types, maybe. Yeah, will be a list of plum types. And then for each field in the struct, we basically push its type like this, because this is a map to type. And we push the type to this thing. And then we lay out them efficiently. So field types dot layout efficiently. Resulting in an efficient layout. Okay, and then we basically reassociate those with names. So this contains offset and layout as a slice. And we would want to turn that into a map of things and layout. So we're actually going to have a map from the field name to offset and layout. And then we want to zip the field names. So struct dot iter with the efficient layout dot iter, and we say fields dot push, dot put, and both dot a dot key, which should be the struct name, the field name, we map that to the layout of that field, including like offset and layout. And then we have this map, and then we return the overall. Yeah, we need to kind of return the overall size and alignment. Yeah. So the overall size is just yeah, it's like we say efficient layout. It just contains basically this size and alignment and fields, that's what I'm gonna call it. Yeah. Like parts, I don't know. Yeah, efficient layout dot parts. Okay. But this entire thing also has a size and an alignment, and then we can return the memory layout. But the size is, the size of the efficient layout, because the entire struct is just this result basically. Yeah, same with the alignment, and the parts will the parts. The kind is memory layout kind struct with our fields map. Beautiful. For the enum, we'll do something quite similar, except the size will be the size of the efficient layout that we calculated. Yeah, that we still need to calculate. Yeah, you know what? Let's first do this. Okay, so basically for each variant, we map each variant to a memory layout. Let's say to an efficient layout. Again, this is weird. Yeah, okay, you know what? This is gonna remain down here. But this is gonna have the payloads, so this will be a slice. Yeah. Of offset and layout. Okay, sure. Alright, so the enum will have, we basically want to build that slice. So just like we have the fields up here, we have the variants down here, which will be a list of offsets and layouts. Okay, so far so good. Yeah. Oh yeah, we want to do something very similar to that up here. So first get the variant types, which will just be a list of plum types. Oh no, we already have those. Yeah, we do have those. Oh, I see. We have a list of slices. Yeah, we can turn this into a map. Yeah, map from string to slice of something. Okay, yeah, that that makes sense. And then for each variant, we basically get the payload types. That's just enum dot variant dot value. There is a key, which is the variant name, and it has a value which are the payloads of this variant. And we take those payloads, we lay them out efficiently, yielding an efficient layout. And yeah, we put that efficient layout into this map. So variance.put variant.key efficient layout. Nice. And now the question is, what's the overall layout? Because that's not as easy as what we did up here. Now we want to get like the total size, I'll just call it size, and the alignment. And for each variant in this map thing, we basically this is supposed to return, let's see, an efficient layout, containing size, alignment, and parts. Yeah. Oh yeah, we move these up here. Size, alignments, and variants, okay. And then for each variant, we lay that out efficiently. We put the parts in there, and we say the size is, you know, the maximum of the current size and the new layout. So efficient layout.size. Same with the alignment, also back here. Okay, yeah, then we have the total memory layout containing size, alignment, and kind of an enum with all the variants. Beautiful, honestly. Yeah, for lambda, what's the layout of a lambda? I think we just have the captured variables, which is a pointer, and a function pointer, which is also just a pointer. So it will be exactly the same as the memory layout of strings. And yeah, for yeah, I think recursive types are kind of difficult. Yeah, recursive types need pointers, but oh yeah, this is kind of difficult, so I should draw something. Yeah, I'm gonna draw something. Okay, so, you know, sizes, well, we have this idea. Each type has a memory layout with a known size. That means that recursive types need to contain pointers. And by the way, they also have to contain pointers in C and Rust and all these low-level languages because of exactly that reason. We need to know the size at compile time to make space for these objects somewhere. And yeah, so we need to know the size of recursive objects. And the question is, where do we put that pointer? Let's assume you have, what the hell? Yeah, let's assume you have some type foo. That's an enum. It is either empty or it's this thingy that then contains a bar and then a baz. And I think memory layouts should be deterministic, which means that, and also independent from each other. So just by looking at this type in isolation, we should be able to figure out a memory layout for this. And the problem is basically, oh yeah, but by the way, this assumed that this down here points up here. If we would just go ahead and say, okay, this is, let's say maybe this also contains not happy with the, this is a struct type of an int, maybe, or even just, yeah, let's say an int and a bar. No, an int or an OR type of that same struct type, which then is either nothing or it's a recursive type. Yeah, that makes sense. So if we say struct types are always the fields of them layouted in an efficient way, then we could say, okay, what's the memory layout of int? Well, the memory layout of int is 1, 2, 3, 4, 1, 2, 3, 4 is this. Boom. And int in memory are just 8 bytes. Yeah, what's the memory layout of this? This is an enum, where one variant is nothing and the other is a recursive type. So this is actually a pointer. This is so yeah, pointer is 8 bytes. So the actual enum would look like this. We have 8 bytes for the payload, because that's the maximum payload of this, which is 0 bytes, and this recursive type, which is a pointer, 8 bytes. And then we also have a tag in here. So you might assume, okay, if we want to put them in a struct, we'll just do something like that. The struct will have a size of 33 and yeah, some alignment of 8. But this is not good, I think. Basically having the int and the payload, which is effectively just a pointer. Because let's assume you really built this kind of linked list. That's what this actually is. You have a linked list that basically this is the an int payload. Let's say we store a 5 in there. Let's maybe draw that down here. And let's build a linked list with a few nodes. So I wanna. No, I just wanted to copy that. Yeah. So let's say we have a setup like this. We have a 2, and the tag is 1. This is like this 0. This is 1. This means empty, or there's more data in the list. This would mean, okay, there is more data, and the pointer can actually point to the next element of the list. And let's say yeah, this maybe contains a 3, and the tag is 0, which means there is nothing coming afterwards, and this is just, this is not a pointer, this is just padding, basically. This seems fine until you realize, hey, what if we have some sort of switch and we navigate into the rest of the list, which has the type, and there we have this nice, beautiful wrapping logic, which basically extends the types at the bottom where they were recursive before. So there we have this memory layout. Hang on. End of an int and a recursive type to this. Yeah, so this is 0, this is 1. empty and more. Okay, so we switch on this and we wrap the type around to this. And you might wonder, okay, what's, and actually like this is probably what you usually think of as a linked list. You know, it's either empty or it's more. And then when you switch on a linked list and you see, okay, it's actually more, then you get back to this. Then you get back this struct that then contains the list item and it contains the rest of the list. What would be the memory layout of this? So it would be an enum, aka we need to lay out the individual children. This child is just nothing, you know, it's size 0 memory layout. This child, well, that's a struct. So we lay out the fields, which is an int and a recursive type, aka a pointer. Int is 8 bytes. So this is an int, and then we have another 8 bytes for the pointer. And that's like the struct. And because everything is in an enum, this is actually the enum payload. If there is something, you know, something more in the enum, and then we have an enum tag that tells us which variant is it. And again, let's assume you have some linked list. No, did that again. Yeah, copy paste, and we move that maybe down here. And yeah, sure. Copy paste, move that down here. Yeah. You know what? For good measure, let's do that again. Another time. Okay. So let's say we have a list that contains 1, boom, and then it says, yeah, there is more content, and the content is here, and then it contains a 2, and it says, yeah, there is more content, and the content is here, and that list then says, well, yeah, there is contains a 3, and yeah, there is more content, and that content is here, and that says, yeah, but no, there is no more content, that I'm actually an empty list. This is how the linked list would look in memory. Well, you see the problem? Here, this tag determines, like this is the payload of the tag. In here, only this is the payload of the tag. Oops. That means that assume we switch on this list, you know, and we see, okay, this is more, so I want to interact with this type, aka this type. Then we're like, okay, what's the memory layout of that? Yeah, in here, the memory layout of this part of the tree only would basically correspond to, hang on, yeah, would correspond to this pointer, just this pointer. I think this is not. I think something goes wrong there. I'm just trying to come up with an example. Let's maybe have. Let's have mutually recursive types, maybe. You know, two enums wrapping each other. Is that necessary? Yeah, I think so. So let's maybe not represent them as these linear things, but just for the sake of it. You know, let's say we have an enum, like maybe say enum foo. No foo. Just say an enum that is either A or B. Okay, fair enough. And then B, in turn, is also an enum that is either C or D, and D contains a foo, and this entire thing is a foo. Yeah, okay, this is a better example. Now just, looking individually at this type, we might assume, okay, this is, an enum as A or B. Yeah, let's maybe say A is an int, A contains an int, and C contains, I don't know, a string. And I'm going to choose a more compact representation here. So we have some sort of enum type that is either A or B, so some tag is in there, and then it contains a payload that is either an int so payload that is either an int or it's something else, and that something else is again, I don't like the representation of this. Hey, we have some memory region where we have this, which means we have okay, I am actually gonna try to do that, print that memory layout explicitly again. Oh man, yeah, we have some enum payload. I don't know how big this is gonna be. Maybe let's work from the bottom down. Okay, so we either have a string, which will be 8 bytes, like this, and another 8 bytes. Okay, so this is a string. Yeah. Oh yeah, let's maybe print the different enum variants underneath each other. And then I have here an enum tag which is either C or D. So this new version of representing enums basically means it's either this top thing with a string data and string length, or it's this bottom thing with just a pointer, because this is a recursive type, and nothing, padding. But of course this enum is embedded in a bigger enum that is either this or it's just an int. So it's either this or an int, which is 8 bytes. Yeah, and that entire thing, making the enum payloads have the same length, adding padding, and then having a tag at the end, which is either A with an int or B with this enum. Okay. So we have some sort of data structure, that has this size, and the data structure tells us, well, I'm either A or B, and I contain either the string data thing or the length. Fine. And now you can imagine like we have that same node down here, and we have that same node down here, and like they reference each other just like the linked list does. So we have a lot of these in memory. And now you switch on this value, on this type, and you get back this type, which means the type wraps around. And then again, like if you switch on that, then it would also wrap around in the other direction, which means that you essentially end up with a type that looks like this. Let me do this on the fly. So it's either C with a string, or it's D with an enum that is either A with an int, or B with, and then C is a string or something, the recursive thing. When this type wraps around, it becomes this type, and the other way around as well. And now what's the memory layout of this? Okay, so this is either, again, let's start at the bottom. It's either an int, so there would be 8 bytes. Or it's a recursive type, aka a pointer. And an enum tag afterwards, which tells us whether it's A or B. If it's A, an int; if it's B, a pointer. And that entire thing is one of 2 payloads. This is the D payload. And there's also C payload, which is a string. And that is this right here. It's, again, the string data and the string length. Like this, string len, and yeah, that, like both of these, here's padding, are wrapped in an enum that tells us whether it's C or D. Yeah, now you should realize something. So, and again, this is a recursive type, so you can think of it like a recursive list with some extra deeply, deep information. Like a lot of these are linked in memory somewhere. Whew. Okay, now we have the problem that this type right here is completely incompatible with this type. I mean, even their sizes are different. This type is 8 bytes here, another 8 bytes, so 16 bytes, plus 2 is 18 bytes. Whereas this one is 8 bytes, 16 bytes, 17 bytes. Well, 18 bytes, 17 bytes. And if you switch on this node of some linked list, this is only one of those types. This other type here is also 18 bytes, and this byte is like all of the nodes of the linked list are memory allocations of 18 bytes, and these are all memory allocations of 17 bytes, and they have completely different incompatible layouts. So when we switch on this type and we want to get into, just inspect this variant, we can't, we don't want to rewrite the entire linked list, all of the data inside of that. That would be kind of crazy. Yeah. So what do we do? The difficult thing is that, as a C programmer, a Rust programmer, you are kind of forced to make it to choose one of these by putting a pointer somewhere in your type. You say, okay, like this field right here should have a pointer indirection, and you explicitly decide where that indirection happens. Here we have two equally good places to do the indirection. We could put a pointer inside of the D, or we could put a pointer inside of the B. Like, these are both variants, or like fields or something along this recursive path of the type. And they are both equally valid. And if we have some global analyzer of the program, that knows all of the types, and especially one that can make these decisions cleverly, that's difficult, I think. Plus, we don't have this. Let's add another goal for the type solving. I don't know, based on a type, you can deterministically choose a memory layout, or like calculate rather the memory layout. I think that's like also a very fundamental goal of our memory layouting, that it's just predictable. That's a very, very nice property. Yeah, so I think we actually need two indirections. When memory layouting a type, we need to check, is this type recursive? And if it is, then we just save a pointer there. That means that we have more pointers. That means that we have basically one layout for the outer thing, A or B, containing an int or a pointer. So int or pointer, and that's like each is 8 bytes, like this. A or B, so 9 bytes. And then inside of the B, the pointer points to a type that is C or D, and it's either string or foo. So here we have the string, the usual string stuff, string len, and string data, pointer, data, and the len, like this, or a pointer to the AB thingy. So either that or a pointer. And this is C or D. Yeah. So rather than having this one big memory part, which is actually like big contiguous dense memory things where we don't have pointers all over the place, they are very useful. They are efficient. That's why we want memory layouting. One of the reasons. Having two pointers of indirection for every linked list node or something is worse from a memory utilization perspective, memory denseness perspective, and information theoretical perspective. But it is something that I believe we have to do to be deterministic and to not favor one of these representations over the other representation. Yeah, so we want to break the memory layouting. Like we want, for recursive types, we want to insert pointers on all of the individual chains in between. Maybe. And actually, I'm just realizing, if you have a struct, I don't know, loop is a struct with A being an int and B being loop. This should be disallowed, right? Because you can never even construct this. In order to construct this struct, you first have to have an instance of that struct. You need a bloop to construct a bloop, which means you can never construct a bloop. So recursive types, they need an enum somewhere in their, chain, which means it would be enough to insert pointers only when we have an enum. Oh yeah, that makes sense. So we have an enum, and for each variant that is somewhere, that has a recursive type that goes beyond this point, that goes up, that escapes this subtree, for each of those we insert a pointer. I think that makes sense. Then we can still have, like deep structs inside of one enum, and somewhere deep inside of that struct we have a recursive type that will still only result in one pointer instead of a pointer in every field. Okay. Yeah, I'm not sure if that was entirely clear, but yeah. It was a lot more like talking to myself and figuring stuff out, because I hadn't considered this. Yeah, okay. But I'm happy with that. Yeah, let's maybe switch back. Okay. So, recursive types. Difficult. Yeah, we will never actually reach a recursive type then, I suppose. Yeah, because for enums, we actually have to check is unreachable. Yeah, for enums we have to check for each variant, is it recursive? Is variant recursive? If yes, just save a pointer. If no, yeah, this. Damn, that is crazy. Okay, so yeah, checking if this is recursive. I think we would just have to, we would have to traverse down into the enum. Like, is recursive. Yeah, enum dot. Is recursive of enum dot field, I guess. Of type. Maybe only of type. Of some type. Yeah. Yeah, just returns a boolean. And we also need to track the depth here. because we basically want to switch on that type, similar to what we did up here. And yeah, for primitive types, the answer is always nope, they're not recursive. Never is also not recursive. Structs may be recursive. So basically want to go over each field of the struct. And if that field is recursive, by the way, depth +1, then we return true, otherwise we just return false. And then for enums, something very similar. So for each variant in the enum, for each argument in those payloads, we want to check if the argument is recursive. And then we want to return, yes, we are recursive, otherwise this is not recursive. Yeah, lambdas, no, they're not recursive. Nope. And recursive types, oh yeah, this is interesting. Basically check if the level is larger than the depth. Larger or larger equal? Let's see, so here we call if variant, but basically if any of those variants is recursive, we want to any of the payloads is recursive. Yeah, then we want to hide only that payload behind a pointer. Yeah, and let's create a for payload of arg in variant value. Do if arg is recursive 0, then stuff. 0, does that make sense? Okay, so if assume we have a recursive thing that points just an enum, and one of the variants directly contains a recursive call that would have the depth 1. Okay, so on that payload we call is recursive of 1, and then we check if 1 is larger or equal to 0. No, so we want to have, first of all we want to pass 1 in here, because that type already has the depth 1 compared to the root type. And here we want to check if the level is larger or equal to the depth. Yeah, that makes sense. Okay, and the second part is like is recursive. I think fine works. Like maybe I want to make a distinction, and then function name of this is not like if there was some little recursion somewhere deep in the type. That's not what we want to do. That we want to check here. We want to check if this is recursive to the root, to the depth that we pass in here. But then again, I think that's kind of obvious from the function call here. Okay, yeah. Oh, but then this pointer type should be normally layouted like any other type. Which means this really should be a memory layout. These should already be layouted. And then we just arrange those already layouted things in an efficient way. Yeah, that makes sense. Okay. Oh, that's pretty cool. That is pretty cool. So this is actually the field layouts. Memory layouts, okay, and then for each field we push field.value, which is the type, and we want a memory layout that, so memory layout. Yeah, and then we have the field layouts, and we get the like entire layout, you know. Yeah, and because here we iterated over the struct, we now iterate in the same order over the fields, giving us the name and the fields. Oh yeah, I mean, this will just have, we already have memory layouts, you know. We could just say this returns an offsets or something. But I guess this is fine. Yeah, okay. Makes sense. And then for enums, yeah, for each variant, we just get the actual payloads, like arg layouts. Very similar to the struct, by the way. So this should be a list of memory layouts. And then similar to how here we iterate over the fields of the struct, we now go over the arguments of the variant, and then we push some layout to that argument layouts thing. So here we have the argument layouts. Yeah, and if that argument is recursive, yeah, then we just push a memory layout that is a pointer. So memory layout size 8, alignment 8, and kind is memory layout kind primitive. Nice. Yeah, otherwise we actually like lay out that memory, the memory of that argument here. Okay, so then in the end we have these argument layouts, and we can just do this. I can't dedent this like I usually do. Why not? That's strange. Argument arg layouts. We lay them out, and then yeah, then we have the overall payload size and payload alignment. Yeah, and the entire enum will have the payload size +1, and it will have the alignment of the payload. Beautiful. Yeah. Tag size. Yeah, if we have more than one variant, we actually need to differentiate between different variants, and then we we use 1 byte for that. Otherwise, we don't need to save a tag. Yeah, that's pretty cool. That is pretty cool. Okay, yeah. I love that. Okay. Yeah. let's maybe compile this. And why is this not working? Expected definition. Yeah, this is what I would expect. Just some other errors, but well. Yeah, 21. So somewhere here. Oh yeah, some erroneous commas. Cool. Now the memory layouting won't actually work, and we don't even use that yet. But the efficient layouting, so I need to do that. Actually, for now, let's just use something simple, let's say. Yeah, maybe let's say we we could, for example, sort the layouts by their alignment. Something like that. And then let's say we have different parts, and this will just be a list of offset and layout, and we track the total offset that we are at. We start at 0, and then for each layout in the incoming layouts, I'm just going to restart. Reload window, please. Hopefully the tab now works. It does. Crazy. No. Okay. Anyways, for layout and layouts, do stuff. Basically, we want to push something to the list. Yeah, we want to push an offset and layout. So offset and layout, where the offset is, well, the current offset that we have here. And the layout is the layout. Simple. And then we increase the offset. Like, Also need to track the size, which is also initially 0, and the alignment, which is initially 1. And then we say, the offset of the entire thing should be a multiple of the alignment requirement for this layout. So layout.alignment offset. Oh yeah, offset equals offset dot round up to multiple of layout alignment. And then, yeah, we push a part with that offset. Nice. Yeah. And then size is well, it's just offset plus layout.size, and alignment is the maximum of the current alignment and the layout alignment. And in the end, we just return an efficient layout with a size, alignment, and parts being the parts list converted to a slice. Cool. Yeah, this is to do make efficient. By reordering things. Yeah. Yeah. Field.is recursive does not work because the field also contains the name, and we just want the field type, which is the value. Okay, never needs a kind, which will just be the primitive kind, I guess. Sure. And then we have layout efficiently. These definitions have the same name, but arguments don't match. Layout efficiently. Slice. Oh yeah, this should be a slice. To slice. Beautiful. Okay, yeah. Size does not exist. Is that specific to the... No, we don't really need that, do we? I mean, yeah, we might need that for these up here. Oh yeah, it's the payload size. That makes sense. And payload alignment. Beautiful. Indeed, yeah, there should be an if here. Beautiful. Okay. Yeah. But we have some naive memory layouting. Next, I think we would need to basically do this. Compile yogurt funds into bytecode. Okay, we can do that. Let's see, we have stuff up here. Yeah, there's all of this object thing, like all of this doesn't exist. Tag object refers to object ID, but that type doesn't exist. Huh. That is interesting. But it makes sense, yeah. Then we have lambdas, sure, and code. Yeah. We don't need this, or this, or this, or this. By the way, this like get an object from a thing with the ID, that's objects are just addresses now, and you just dereference the address to get the data. It's yeah. So no universe, no scope for the objects, and no hash, and no none of this, at all. Yeah, that just doesn't exist. Cool, I think. Yeah, printing bytecode instructions is interesting. I think that should go to the VM as well, because this is where the bytecode instructions are now defined, you know. Yeah, so we can write the data that we defined above, and then we have the actual execution stuff down below. And the VM is like pretty short right now, and it's gonna stay that way. So yeah, that's the core loop. Like every code that you write goes through this loop basically, which means we somehow need to think about what this returns. Probably just an address. And we don't make a universe, we just allocate memory for the thing, for the bytecode. Phew, okay. Yeah. Ugh. So we compile yogurt into an address of the main function, and at that address there will be bytecode instructions. Yeah. So I think we'll actually need a lot of space for the instructions. Let's just hardcode something. Like this doesn't have to be perfect. So instructions is just going to be an uninitialized slice, let's say. Bytecode instructions. I don't know, 200 instructions. Sounds good. Yeah, we don't need this. Or, yeah, this, we need that. Signature to address. Crazy. Maps the signature to the address where the bytecode instructions for that function are. Okay, and then for each function we basically put in there. Oh, no, we can't do that because we don't know how big the functions will be. We don't know that yet. Yeah, so rather than doing this up front, we would have to do that. We would have to do that while we are compiling the functions. And then the question is, well, if you call some other functions, we already need to know the address of that. And the way it's usually done is you have a 2-pass compilation to bytecode. First, 1 pass is just going to convert all the instructions of a function to bytecode, except the calls. For the calls, it just says at this position, there's a call of this other function with that name, that signature, and you put a placeholder in there. And after every function has been compiled and we know the location of each function, we know the address, now you make a second pass and you patch all of the calls. Right, so signature to address, well, we don't know that yet. And then in here we have for each function in our functions. Yeah, we don't do this. We don't need this. No, we just get the signature and the function. Yeah, and then we put that in here. Makes sense. So signature to address. Yeah, here we put the signature. Oh yeah, basically we need a cursor through this thing. Hang on, for lists we can also, can we reserve memory for lists? I think we can. Uninitialized. You can create lists. Reserve uninitialized. Okay, yeah, so the list is not initialized with anything, but we can, oh, it's find on a list. That makes sense. Okay, so we have a list, and then we call instructions dot reserve uninitialized 200, and then we can push 200 instructions, and it's guaranteed that these won't be relocated. It's gonna bite us in the ass, I think. Yeah, having this hard-coded to a quite low number, I think, maybe. Anyways, yeah, signature to address is just an empty map, and then we iterate over all of the functions. We get the signature, we get the function, like the actual function body thing, and in here we just put the address that we're gonna write the next instruction to. So this will be list dot the underlying slice is what we're gonna get, the data, and then we're gonna ask get ref of the list len. So from this typed slice, we're gonna say, hey, please give me basically the next item that the next instruction would be written into. Yeah, and then that is going to return an ID. Not sure what that is about. Don't have that. And then we just say funds dot no. We just say fun.compile signature, and then instead of this and even this, like yeah, instead of this we just pass in the instructions, like a mutable list of instructions. And we also need to have patches. Like while compiling a function, we may find other calls, and we should say, hey, this, like bytecode, this bytecode instruction, this is like a reference, a pointer to a bytecode instruction that needs to be patched to a call to this yogurt signature. Crazy. So rather than passing this around, we just pass around the patches, and the compile thing can add patches if it emits a placeholder that later needs to be patched. Yeah, and we don't need this, and instead we just say for each patch in these patches, we basically patch them. So oh yeah, list means that it contains maybe a tuple. Yeah, so this will be a reference to a bytecode instruction, and we're going to set that bytecode instruction to a bytecode instruction dot call of an address, of a signature to address, getting the address like of the signature that we actually want to call here. Okay. Yeah, and in the end we just return the address of the main function. Nice. Yeah, in here we don't have code or universe or something. No, we just have compile of signature, instructions. Oh yeah, instructions is important. Instructions will be a list, mutable list of bytecode instructions, and the patches will be a mutable list of tuples of bytecode instruction pointers, references to the signature that we want to call. Not beautiful, but at least hopefully workable. Yeah, and this returns nothing, actually. Doesn't need to return anything, it just appends stuff to this. Okay, that is beautiful. Okay, yeah. And then before actually looking at the function content and compiling that, I'm gonna take a small break and make some more tea. Okay. Yeah. Somehow need a plan of what do we do with arguments? How do we like get captured variables? How do we represent like the intermediate temporary variables? For now, I would just say let's put all of them on the stack. Yeah, on the heap. Sorry. So yeah, we need some sort of a stack model that is true. Yeah. And I guess this right here is only to have a different behavior for closures. And that is important. Although I don't quite know how we're gonna do that. Hang on. Yeah, let's maybe switch that around, right? Like if you call a closure, then you put the arguments for the closure, you put them on the stack. And then it's kind of silly to then try to put the captured variables before those. So before we would probably, hang on, is there like a lambda call? Yeah. Not sure what's going on here. Hang on. Oh, yeah, I think the lambda call instruction was like really expensive in the VM, because it would basically pop this many arguments, then push all the captured ones, then we push these arguments and then actually call the closure call. I think if we just flip that around, if the closure, if lambdas accept the explicitly passed arguments parameters first, and only then the captured ones, then that makes more sense. Yeah, okay, so righto, we have the parameters, we put them on the stack. And here I would mention that this will probably contain a yogurt ID for each byte, maybe? Oh, that seems kind of wrong. You know what, let's maybe back off. Let's say we have, this is a map, maybe. A map from yogurt ID to an int in the stack. Well, you know what, even better, let's maybe have a separate stack model struct that contains the mapping from yogurt ID to int, and it contains size, len, I don't know, which is the current length of the stack. And the stack model would then just create a stack model with an empty mapping and a size of 0. Right. And then each parameter would basically need to be pushed on the stack, and that's they get accepted as either pointers or just immediately the values that like the you know, the values directly. That would be better, but also a bit more difficult, I think. Yeah. Actually, no, I'm not certain what would be more difficult. Yeah, you know what? Let's let's pass them on the stack directly. So basically the idea is the following. You call some function, you have a stack of bytes with some stuff on there. And I should also document that somewhere up here, perhaps. And this doesn't, the file name and everything here doesn't make sense, but maybe converting bit to bytecode. Nope, no longer true. Nope, nope, okay. Okay, so yogurt is converted to bytecode for a low-level virtual machine, but not the LLVM. Yeah. I know I have mentioned LLVM before, but in case you're wondering, that's just a compiler framework, yeah, where you basically don't have to write the back half of your compiler, but instead you just compile to some other code. Some LLVM IR is what it's called, and then you let LLVM take care of compiling that to actual machine code, which is interesting. I think it does kind of take takes the fun out of building a compiler, at least a bit, you know. Sure, you have the language semantics, which are the most interesting part. You have control over them. You only automate away the backend, and if you want to have a production-ready language that works on multiple computers on different architectures, that is really highly optimized, which LLVM is also great in, because there's a lot of research going on with LLVM and so on, then that's fantastic. You know, if you can use LLVM, use LLVM. It is kind of bloated sometimes. LLVM is huge, and it's also quite slow, because the optimizations were written mostly with the performance of the compiled program in mind, and not the performance of the compilation itself. So yeah, stuff that compiles using LLVM is often not, it just takes longer to compile. Right. Okay. Also for our case, the entire idea was that you could compile new bytecode on the fly, that you could just create, hey, this is some new bytecode, please compile that, and then you just continue running and you can directly interact with that. And this idea of this granular recompilation, we could invoke LLVM every time, but that would also mean that for running your program, you would need to ship LLVM. This is not just, we don't have the separation of, we have a development machine and then you compile something to some executable and then you just ship that tiny executable out there. But instead, the compilation to a low-level code, sure, that happens on a machine, you control on a developer's machine, but the compilation of that that low-level bytecode to an actual machine code, that has to happen on user machines, because the code can generate new bytecode on the fly, and we don't want to use LLVM there, so we need to have our own compilation stack anyways. So there's nothing, we don't win a lot of there. But we could maybe say, hey, let's use LLVM, and then also write an LLVM backend to some custom thing. Then we at least we use all of the optimizations that LLVM implements. But yeah, I don't know. I don't see the immediate appeal for Plum, at least. For most ahead of time compilers, this definitely makes sense. But yeah, again, for Plum, I'm not sure. Yeah, that's basically what LLVM is. And initially, LLVM stood for low-level virtual machine, and by now it just means nothing. Yeah, the name LLVM itself is not an acronym. It is the full name of the project. LLVM has little to do with traditional virtual machines. So, yeah. Right. So, yes. So to do this, the low-level, or the bytecode and VM can be found in vm.mar. Yes. This file contains the code that compiles URIT to bytecode. A big question is how to represent values. Currently, aka hopefully when this is done, we use the memory layout.mar file to calculate reasonably efficient memory layouts for all structs, for all types. If possible, we save values unboxed, aka not behind pointers. So previously, even in the C code that we compiled to, if we had a struct, then each field would just be a pointer to another type. Here we don't have that. If we have a struct containing another struct containing another struct, all of that will just be next to each other in memory. Really efficient. So yeah, if possible, we save values unboxed. Great. And on the stack, calling a function when you call a function, the function expects the arguments to be on the stack. Yeah, the order is kind of, how do we deal with that? I think, like, if you pass an int and like a byte and an int and another byte to a function, we do want them to be aligned. So let's see. I think we just want to have the same layout as if we would, put them in a struct, as if we did this right here. I mean, we can do this right here. Example, yeah. Like, here's an example. Foo takes an A, which is an int, or A, which is an int, B, which is a byte, C, which is an int, and then it does things. Yeah, I don't know. Let's say D. Why not? And just returns an int, which is A plus B. yogurt. Yeah, here's an example function. Its yogurt looks like this. Now I'm actually just going to get inspired by this. Now something like this, I guess. Yeah, no. So this is called foo. Int byte. Yeah, contains 0, or it accepts 0, 1, 2, and 3. And the first thing it does is it calls. In fact, that's the only thing it does. Yeah, that's me. Oh, I guess let's switch this around. Let's say A is a byte, B is an int, C is a byte. Then we have, this should highlight the memory reordering that we want to take place. And then here let's also have a constant so that we see how that works out. Yeah, in yogurt, its yogurt looks like this. So we have a byte, an int, and a byte. Yeah. Yeah. Then we create a comp time 5. Perfect. And then we call something. Oh, this is a lambda call. Yeah. Now we can call a comp time known function. So call plus int with 1 and 3. And this results in 5. Perfect. Okay. Yeah. The calling convention looks like this. The calling convention is this. The stack has to be when a function runs, the stack has to be aligned to 8 bytes. That's the first part. Second part is all arguments to the function should be on the stack as if they were laid out in the struct. Yeah. For our function foo, this would be the stack if called with, I don't know, 9, let's say. For call foo and then byte int byte, let's say 1, 2, 3. This would be the stack. And this is B, all of this. 1, 2, 3, 4, 1, 2, 3, 4, perfect. And then we have a byte, 1. This is A, and then we have C, which is another byte, perfect. This will be the stack. And then we have padding, 1, 2, 3, 4, 5, 6, actually, like this. Yeah, sure. I'm fine with it. Then oh, there. By the way, if you're wondering why 8 bytes, we don't have any types larger than with an alignment requirement that's larger than 8 bytes. So I think that's also true for like modern computers. You have alignment requirements of 1, 2, 4, and 8, and that's it. No. Yeah, there are some cases where you need memory with more alignment. So for example, there are some syscalls to make memory pages executable, and they need to receive memory pages that are aligned, or like memory pointers that are aligned to a page size, which is a completely different topic, but yeah, like for normal data types, ints and so on, 8 bytes is the maximum alignment you may need. So it's fine. I think it's fine if we just say functions need to be aligned. The stack needs to be aligned to 8 bytes between functions. Actually, I think, hang on, for, what is it, x86 calling convention, the stack actually needs to be aligned to 16 bytes. I'm not entirely sure. The order in which, yeah, the calling convention is basically the order in which parameters or things are allocated, yeah, and how they are passed, like on the stack. In registers or mix, we only have the stack, so that's easy. Yeah, we don't have registers, and we don't have this. Hang on. Yeah, cdecl is the typical C calling convention. Doesn't say anything about alignments. Ah, yeah, here it is. Yeah, it must be aligned to 16 bytes. 16 bytes. That's crazy. Yeah, anyways. So that's the... I think we're gonna go with 8 bytes. And that means that when we would later on need to call C functions, we need to take care of aligning the stack and bleh, pain. But for now, it's easier that way. We could also say we don't care about alignment at all right now and just put the arguments on the stack packed, and that's it. But I think it's actually not... It's not hugely more effort to do it like this. So, yeah. Okay, so this would be the stack. Yeah, each local expression, I guess, which by the way, this should be 4. Each local expression, in our case, 3 and 4, are allocated on the stack, are expected to be on the stack after they are executed. Seems reasonable. For example, after the comp time 5, and then we have the stack here. That's maybe, this would be the stack. Yeah, I should call this 1. Yeah, that's cool. Yeah. And let's maybe copy this in here, and then say after the comp time 5, this would be the stack. 1, 2, 3, 4, 5, 6, 7, 8. And then this is the at 3 expression. And then the 4. Yeah, the call to plus first pushes all arguments to the stack. Like this. And then it has 1 and 2 in there. Yeah, which means we basically need this again on the stack. 1 and, hang on, 1 and 3. And 3 is this comp time 5. So basically this part right here. Call the plus first pushes all arguments to the stack. After plus completes, stack will look like this. Stack has to be aligned to 8 bytes. All arguments to the function should be on the stack as if they were laid out in a struct. Also, after a function returns, the arguments should have been consumed from the stack. And what else? Yeah, after a function returns, the arguments should have been consumed from the stack. And the only remaining data should be the return value. And replaced by the return value. Yeah, after plus completes, the stack will look like this. Boom. And then foo cleans up the arguments so that the stack is this. And then basically just that part. Yeah, that's the idea. Yeah. Then it calls plus. After plus completes, the stack will look like this. Perfect. Beautiful. So let's do that. We compile this. We have a stack model, which tells us where is each ID on this like virtual stack, you know, and what's the size of the virtual stack. So we expect that the parameters are there, which means in this stack model, we need to be able to push a parameter, body params. That's probably like a params. Body params is a slice of yogurt ID, because of course it is. And the yogurt IDs reference the surrounding function expressions, which then contain types, where we know the memory layout. Okay. So layout parameters on the stack. So param layouts, I think, would just be memory layouts. And then for each parameter in the function body params, this is an ID. We get the corresponding type, like this. And then we get the memory layout for the type, like that. Fair. Yeah. Okay. Yeah, we can do that. Sure. Oh, yeah, and we want to push that param to that, so that then in the end we can say param param layouts.layout efficiently, which returns us a layout. Mm-hmm. Yeah, expected an equals sign. Yeah, I know. Yeah, we just assume that they are on the stack. So, oh yeah, we can get the parts. Like maybe first lay that out. And then for each memory layout part, we know the offset. Oh yeah, and we add that mapping to the stack model. So stack model dot mapping dot put the offset. So that this mapping basically contains, hey, parameter, parameter 0 is at offset 8, parameter 1 is at offset 0, and parameter 2 is at offset something. Okay, yeah, like that. And also stack model dot size is layout dot size dot round up to multiple of layout dot alignment. Oh no, hang on, to 8, because that's specified in the calling convention. Beautiful. So initially, the parameters are on the stack. Yeah, we need to think about closures. For now, we just panic there. And then and then we basically compile the body into instructions. Oh yeah, but not like this. But we can just pass the instructions from up there down here. Okay, yeah, we have instructions. We have a stack model, beautiful. We have fun. We don't have code or the universe or this, but we do have patches. Yes. Okay. Okay. Yeah, again, I'm not sure about captured things. Yeah, to do. Think about this. Okay, yeah, in the end we just return something, but we don't really need to, because, I mean, instructions, nope, we don't need anything. Beautiful. Okay, now onto the actually crazy part. Compiling a function body. Given a list of instructions, giving a function, ignoring this, having a list of patches where we can just add patches from containing what? Bytecode instruction, pointer, and a signature. Makes sense. So bytecode instruction, pointer, and a signature. Cool. And then we could also just name this patch. But, well. Then we go through the IDs. We see, okay, we get something from the function. We switch on the expression. Sure. Yeah, parameters can't be reached. Uninitialized means we don't need to do anything. We do need to adjust the stack model for all of these. Yeah. Okay, we can do that. So let's maybe start with this. I think this is the simplest one. So if there's a comp time value, then we basically need to emit instructions that put that comp time value onto the stack. And this is already, it can be difficult. Yeah, because converting a value to an object is not something that the bytecode knows. I think. Like I think we might actually have to. I think it's easier if for now we just save a pointer for each object. Yeah, okay. Let's do that. So. Ooh, that probably means that we would also have pointers for these. I don't like that. I don't like that. So my thinking is, what if we have, you know, some point with x and y? Oh yeah, we would basically have to emit instructions that then push, like, I don't know, in the code you have something like point x is 2, y is 5. We would basically have to generate instructions like push 2, push 5 that result in the thing on the stack being this. So that basically on the stack you have this struct. That's the idea. How would that even Yeah, I think that's actually the way to go, to just emit instructions that then create these objects on the fly. Crazy. Ooh. But then the next question is, what if it's like a really complicated object, and we actually need to, you know, create new memory for that and so on. Oh, but we can still figure that out, right? I'm just gonna copy that somewhere down here, probably. To object. Yeah, you would value to instructions, actually. Yeah, we don't have this. We don't have this. Why do we need that? Oh, for lambdas. Something. We'll figure something out. This, like, currently lambdas will just be a to-do, and converting a value to instructions basically means that we, if it's an int, yeah, okay, so we need instructions. Okay, so far so good. Then we want to, you know, for an int, we just want to not allocate memory for that. We'll just add an instruction that pushes an int. So a bytecode instruction, push 64 of this int. Yeah. Okay. Yeah. For strings. Ooh. Yeah, now we need to allocate memory. So I'm not, how would that even, let's maybe print examples. 5 becomes yeah, and the stack is then basically this. Okay. And then for string, the question is what's going on here. Basically, we want to do this. Hi becomes. Let's first figure out the stack. Yeah, we want a pointer. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. I don't know, something. And then 2 is the length. So actually, something very similar to this, except 2. And yeah, the last one can just be this. The one before would be push. We basically want to call malloc, right? So first we need to say how many bytes we want to allocate. Then the alignment, 1. Then we call malloc, which pushes no, it pushes the address onto the stack. And then we can print like a live stack behind these. That's amazing. So 2, then this, and also this, then perhaps something like this, malloc, then we push 64 from stack 0, yeah, that would just push that same address again. Then we do push 8 of the letter H. Let's actually like see what byte that is. Lowercase h is that like a hexadecimal hex version for that? Yeah, there is. So h is 6-8 in hex, 6-8, and I is, oh yeah, because then right next to each other. Hi. Okay, so yeah, this is actually gonna be, hang on, 6-8 will be that, and later on, no later, just do this, store 8, which will then consume a byte and an address, and will store the byte at that address. Ooh. We also want, yeah, which basically just results in that same thing. Now we want to repeat that, but we also want to add 1. And I think the consistent thing is to just always add a number, even if that's 0 up here. So push 64 0. Well, 3, 4, 5, 6, 7, 8. And then an add instruction, which means that, yeah, okay, we're basically back at this. But then down here, this will actually be push 1, and then this will be 1, and then this will be 3, and this will be 1, 3. Yeah, followed by this, storing that. Beautiful. Which means in the end we just have the pointer here, and all memory at that pointer is initialized. And then we push the length again. Yeah. Okay, so I am aware that this is not super efficient. Just from a space perspective. Because if you have a long string, then it's not just that the long string will be somewhere in memory, like in your compiled program. You will actually have several instructions for each single character of the string. Yeah. Yeah, okay, so how do we do that? Yeah, we do want to push instructions. So I guess instructions.push, bytecode instruction push 64 of the string len. And then we push an alignment 1. Then we push, what we call malloc. Then we push this from stack from position 0. Oh yeah, but we do that for every character. So for char in string.chars, do push the pointer and then push the index. And then add them together. Then push the actual character byte. I think a char has a byte. Yeah. Okay, and then store 8. Okay, and then finally in the end we push the length another time. I wouldn't say it's beautiful, you know, having 5 instructions for every character, but it should work. I mean, we could of course also just actually allocate memory for that. That is far easier. Far easier. Yeah, let's do that. Yeah, something. Yeah, okay, never mind. We have the string right here. We can just hang on, push the string instructions.push, just push 64, and this is the string data, and also the length. Easy. Oh yeah, doesn't need an address. Convert the address to an int. Okay. Then the struct. Yeah, here we basically what do we do? You know what, for now let's just put a to do in here. And for the tag as well. And for the type as well. I see padding here. Let's just get 2 plus 3 working, and we can continue from there. Okay, so we have this. Next, 2 instructions. You can convert a yogurt value to instructions, and that will actually push the value onto the stack. Beautiful. Yeah, we get the expression, sure. The thing is, the expression will then be at the stack at this exact position. So in the stack model, we can say, well, I think this is a more common thing than we realize. So let's also have a line 2 of a stack model. Let's have something like this, and then here we can say stack model dot align to 8. Beautiful. This doesn't work. This expects lines. Yeah, indeed. Indeed. Yeah, here we say stack model dot align to. Yeah, okay, we get the expression. The expression has a type. We have a layout, which is that. We align the stack. And then in our stack model, we add a mapping from the ID to the stack model size. This call doesn't work, okay. Oh yeah, because stack model is supposed to actually be a stack model. Sure. Nice. Yeah. I mean, that's pretty cool. Now the only thing required to do done. Oh yeah, here we need to do padding to the stack. So basically for each byte in the type, we could say we push the bytecode instruction dot push 8. Yeah, we'll just push 0 bytes there. Yeah, basically as padding. Because we assume that this uninitialized thing returns, or that it has a certain size. And it uses that size on the stack. Okay. Then comp time values, they just get converted into a series of instructions that then end up producing that value on the stack. Okay, structs, I don't know. We'll probably have to memory layout the fields, and depending on the field, maybe take the initial. That's interesting. I think we want to guarantee that the fields are, like, let's say you create a struct with fields foo and bar. I think the order of the fields matters. If foo is a function that panics with some error, and bar is a function that panics with another error, just because panics are the only side effects we have right now, then we should panic with the message that foo says if the foo line comes before the bar, and vice versa. So that means that the instructions from the fields need to be pushed in the order that the fields were in the code. I mean, currently that doesn't happen because I think this is a map and not a list or something, but yeah, we should do that, and then we should reorder the fields to match the struct's memory layout, and then remove the intermediate field values, or at least some of the field values, depending on whether that coincidentally matches the thing, like the layout of the struct and so on. Like, there's lots of opportunity there to build something that's quite efficient. Okay. For now though, nothing. We do nothing here. And also for member functions, like accessing a struct member. There's also nothing we currently do there. Same for tags, same for switch, same for lambda. Oh, let's maybe put those in there so that we have a hint where to go if things turn up bad. Okay, yeah, lambda calls. These will be super interesting, to be honest. Yeah, normal calls. Yeah, we need them, I think. We might need them. Okay. So yeah, we definitely push a call instruction, but we don't have this, but instead we add that to the patches. So patches dot push tuple from instructions dot get ref to something like this. Get a reference to the thing that we're about to push. And then, okay, how we can also just do this. Get ref instructions.len -1. Yeah. And the signature, which will be the receiver. Yeah, and then we need to adjust the stack model. Though not really actually. Not really. Right? I'm not sure. Depends on how we do this. So this is definitely a to-do. That we also need to resolve right here. This is probably where things will crash. And then we have the instruction, which is just very similar actually. Yeah, depending on the instruction, we do different things. So add ins would emit add 64. Sub would call what? Yeah, multiplying ins, dividing ins. Modifying ins, taking modulo of ins. Yeah, and or XOR. Compare is somewhat, I'm not sure there. Probably makes sense to do something about that. Yeah. Concat strings also doesn't have a bytecode instruction. Yeah. Okay. Here we need the arguments first. Yeah, I mean we crash here anyways, so yeah, and then we don't have this. Hang on. Where is this happening? Oh yeah, here. Yeah, that makes sense. Okay. and we don't have this. Because we had that at the beginning, before the switch. Yeah, then we push the returned thing again. That's a big to-do. And that as well. And these as well. Function, what's it called? The top part is often called preamble, so I guess post-amble? I don't know. Yeah. Okay, so we can convert a value to instructions. I think the next useful thing would be to basically copy a thing that was on the stack, somewhere before on the stack, and copy that to the top of the stack. Yeah. Yeah, I'm gonna take a short break. Okay, so let's just see where this breaks. Or if this even compiles. It does compile, okay. Right, we don't even use that code yet. So, and we don't even import that. Well, okay. Maybe it does not compile. Yeah, what we want to do is not this, or this, although that's pretty cool. We want to try to do this. Oh yeah, not to C, that's also old. We could remove, yeah, I'm gonna remove the C file for now. Is that even imported? No. Okay. Yeah, something like this, yogurt.compile, and it doesn't need anything, I think. Just compile the bytecode, and the main should just be an address. And then we could run that address, the bytecode at that address. Super safe. Yeah, list is not in scope. And universe, list is not in scope. Yeah, now it tells me errors. Interesting. So stack model.mapping.put. Oh yeah, that needs two things. It needs the ID, which is the param. Probably. Oh no, we need to live efficiently that. Yeah, we need to zip the params, so fun.body.params.iter with the layout parts, and then we have both dot A and both dot B dot offset. Beautiful. I have for both. Nice. And maybe let's also like have a function add mapping or something. You know, add. Maybe not. I don't know. Yeah, let's add that add mapping of ID and offset. And just model.mapping dot put ID. Oh, hang on. Model ID and offset like this, and then there's also add mapping of an ID without an offset, and that will just add the current size. So model dot add mapping ID model dot size. Yeah, I think that's nice. Then in here we could just do model dot add mapping. Well, okay, it's not like we use that in a lot of places, but still, it's nice. Yeah, and here we just yeah, sure. Okay. So then what do we do here? We take the functions, we put the corresponding address onto the signature, which means we would have to get something from the instructions list. This does not work, okay, because we have a yogurt signature and a map of bytecode instruction. Yeah, that is technically correct, but there are multiple instructions there, so we just save an address because that feels a bit more clean. You know, a reference usually only refers to one instance of the thing being there. Yeah, this needs that. Yeah, I guess that's true. Yeah, okay. Yeah, this is for initialize at a plum type. We can't. That is true. Yeah, there should be 0 to layout.size. Beautiful. Then down here we have instructions.push, bytecode instruction.call with yogurt fun, but it needs an address. That's true. Yeah, for now let's just put nothing in there, and I think that does make sense, but oh yeah, with an int, but it needs an address. That's actually null. Yeah, Martinaise says null. It's the $1 million mistake. I think actually that's just a global variable that standard lib var null. Yeah. Null is just 0 as an address. I mean, sure. Okay, so we have null. Next, stack model.pop. Oh yeah, I'm not sure what to do about that yet, but we're not going to reach that anyway because of this. So let's see where we fail. Oh, and it doesn't even compile. Did not expect that. Oh, because we have a mapping from yogurt ID to something, and yogurt ID does not implement hash. That is a fair assessment. Does it implement equal? Yeah. Okay, so it is just a wraparound. An int. Correct. Yeah. So we can just hash the int. Yeah, hash. Oh yeah, hash takes a hasher and an ID. And returns nothing, and that just is hasher dot hash ID dot int. Beautiful. Yeah, this is double things. That does not look correct. So 1, 1, 3 and the universe, I think. Oh yeah, instructions is already a list. Sure. Yeah, we need to implement calls. No surprise there. Yeah, and the thing we need to do is we need to push the arguments of the call to the top of the stack. And we know that they already are somewhere back on the stack, because these are previous instructions, which means that for the stack model we can find the distance. We should be able to find them there. Yeah, we just need to copy them somehow. When the stack just contained objects, that was pretty straightforward. Like, just have one instruction push from stack, and that pushes the object to the stack. But now, let's say your stack contains, like this is a complicated thing, like a point or something, or a range with from and to, and those are both integers. So there are actually 2 integers on the stack somewhere, and you need to push both of them on the stack again. So you kind of, depending on the type of the argument, you need to fetch all of the individual fields and so on from further back on the stack. Yeah. Yeah, how can we do that? Let's maybe we do something similar here, don't we? Yeah, where for the that makes sense. The parameters that a function expects, they should have the same layout, memory layout, as the arguments that we push on the stack before we call the function, because they are the same thing essentially. So here we have layout arguments on the stack, and this means we have the arg layouts, which will be a list of memory layout, and then for every argument and the call arguments, we basically get that argument, get its type, memory layout that, push that to this, then we lay out all of them efficiently, and because memory layouting is deterministic, this will result in exactly the same same layout as the actual layout that the function expects. Okay, yeah, and then we have these right here. So for both in zip do. Now, so what we do here is we take the arguments. Oh yeah, we add mappings in stack. We don't need that, I think. Oh, not really. I think we basically want to go the other way around, right? Instead of going over all of the arguments in like the order that the arguments are passed, or like declared in the function, we instead want to go over them in the order that the function expects them in. So in the order that the final memory layout will be. And then for each argument we will just push that to the stack somehow. Yeah, okay, so I think we need, yeah, this makes sense. That's cool. This one right here, not so much. Here we actually need to go over args in the layout order, not the semantic order. Yeah. Okay. So how do we do that? I think we need to, I think it makes sense to have some function for basically copying an argument from further back on the stack, which will be similar to this one, except it doesn't take a value, it just takes, I guess, a type like a maybe even a memory layout, just like type, sure, like layout. Yeah, we want to copy something, a value of this memory layout from further back in the stack to the current position on the stack. Yeah, please emit instructions to do that. That makes sense. Okay. Yeah, we need to know the offset at what that is on the stack. And then I think we can just we should switch on the layout, right? Yeah, because all depends on the memory layout. Yeah. Okay, so memory layout. Ooh. Is it enough to just like not recursively traverse down into the type, but just say, okay, there's this size, so let's just copy that many bytes from further back in the stack. I know that the stack direction, yeah, whatever that's called, and the and the stack the endianness of ints is unspecified, but we are not actually inspecting those or loading those ints. We're just copying raw bytes. That should work without that. So I think we can just say for, I don't even know, byte in layout.size. We push a new instruction, basically bytecode instruction dot push 8 from stack from that offset. And that's it. Right. Yeah, that should be it. Yeah, if we have like some really, like, I don't know, 50 byte huge nested struct thing somewhere back on the stack, and now we want to pass that to a function as an argument, we can just copy those 50 bytes onto the stack directly without even inspecting them, without doing anything with them. That should work. Okay, yeah, so that's actually not the difficult part, apparently. Yeah, what will be a bit more tricky is finding the order in which we want to put them on the stack, the different arguments. Yeah, this right here, because let's say like the arguments, they can be arbitrary expressions, and yeah, we had this thing, find reference to or something. Yeah, find distance from top. Sure. Well, we basically want to, by the way, let's put that to the stack model here. Yeah, makes sense. Find distance from top. We have a stack model and an ID. I mean, we don't need any complicated stuff. We just say, well, we take the current size, and from that we subtract the mapping. Yeah, that should be the distance. If there's a mapping that says it's exactly here, then that's 0. Totally fair. And the top is the size. Okay, so mapping is not in scope because this is model mapping, of course. Okay, find distance from top should now work. And that means that in here, can we sort things? I'm not, like we don't have higher order functions in Martinaise. Is there some sort? There is no sort. Hang on, in memory there's slice. Is there a sort in here? Okay. Size of t. Oh, I see, as long as these t's are comparable, right? Yeah, as long as the t's are comparable. What are our t's? Our t's are... And we kind of also need the index of... Yeah, that's kind of bad. Yeah, let's maybe, instead of parts, let's maybe put 2 things in there. Let's say efficient layout. Sure, it has a size, has an alignment, and it has basically an arc or part to the index. Inputs to part, something like that. And then part to index, to input. Something like that, which goes the other way around. Maps. Oh yeah, let's map input. Input to offset could just be that. Input to layout is not really, like, we have that here. Yeah, input to offset, beautiful. Inputs sorted by offset, I don't know, something like that. Maps input each input by index to its offset. Yeah, this is self-descriptive, I think. And then we have the inputs. Okay, and then we have this, which is just the parts, which will actually be twofold. So we have input to offset, and we have inputs sorted by offset. Oh yeah, for now these will just be the same thing, by the way, because we order them up, like, in the same, we don't reorder them. Well, yeah, so here, input to offset. Yeah, here we just save the offset. And then also in inputs sorted by offset, push import layout is input item and input index is this. Yeah, sure. So then the offset is that, and then yeah, basically want to do this. I mean, this is not really constructed or used anywhere. It's just okay. This call doesn't work. Push. Offset layout. Oh yeah, no, this should just be a list of int. So that down here we can say, yeah, input to offset. And input sorted by offset is input sorted by offset converted to a slice. Beautiful. And then, well, not really, but and then the efficient memory layout is used somewhere up here. Yeah, here. Where we take the struct fields. Oh yeah, because this contains offset and layout. You know what, let's just say we have a struct layout and the enum layout. That seems reasonable. Yeah, struct layout is just field to offset. We have field to layout. We have fields sorted by index. Nay. Okay. Cool. And then for enums, something similar, I think, where we basically have the variant to offset to arg offsets. Variant to arg layouts. All right. Yeah, this needs to be a slice. And then we have let's maybe also have a variant layout. I think that's better. Yeah. Variant and then here we just have the arg offsets, which is actually simpler than, which is basically this, but instead of mapping from string to this thing, we just have a slice. Yeah, that's better. Args sorted by index. And then in here we have the variants, which will be a map from string to variant layout. And we have the tag offset, because why not? And even if there's a tag size, that's also, you know what, tag size is also the same thing. Like, this is everything you may need to know about enums. I think that's pretty cool. Okay, so for structs, we have field layouts. which is beautiful. Yeah, and then in here we basically want to build these. Field to offset being a map from string to int. Field to layout being a map from string to memory layout. Yeah, fields sorted by index, interesting, will be, you know what, let's just make a slice of the correct size, because why not? Or like struct dot size, is it? Something like that. Yeah, and then in here, for each of the struct fields enumerated, and this is a beautiful, beautiful case of putting the do in the new line, and this is why introducing keywords are fantastic. Yeah, zipping that with efficient layout. Oh yeah, input to offset. Yeah, we have maps here now. That's actually useful, I think. Yeah, no zip needed. You know, that's yeah, I guess let's just say we have the field. Now, it has a name, which is that. It has a type, which we don't actually need, I think. Oh, yeah. Name is the item value, item key. And then the index is the field index, like this. That's what enumerate goes, so something with index and item. And these are map entries with key and value. Okay, and then what we do is we want to fill these. So basically, field to offset, we want to put the name in and the offset. And the offset is just, you know, efficient layout, or just layout, I guess. Yeah, layout. Layout dot has some things. Layout dot input to offset, and getting the thing from the index. That's beautiful. And then we also have inputs sorted by offset, but that's also nice. Yeah, okay. Okay, field to offset, then field to layout. Means here we put the layout inside, so this would be field layouts get index. Then we have fields sorted by index, which should be probably no, there should be slash to string, shouldn't it? Yeah, there should be. And not push, but not put, but push. And actually, yeah, let's maybe say fields yeah, I don't know, fields, why not, is a list of strings. And then we do some layouting, and we say fields dot put this. Yeah, let's maybe do this. Lay out the fields individually. Beautiful. I like lay out the fields. Build up, or like calculate derived info. Beautiful. Okay, so here we have the field layouts, where we'll just iterate over the fields. Yeah, and we push the field struct get field, gives us a type. Yeah. The memory layout of that, and we lay out all the fields, and then we calculate derived info, field to offset, field to layout, fields sorted by index. Amazing. And then here we can just say fields dot iter dot enumerate. Yeah, we have the index, we have the field name, which I guess is just the field. Yeah. Yeah, we have fields to offset, we set that, field to layout, we set that, and then in the end fields sorted by index. Should be this. And I think here we just yeah, this one has inputs sorted by offset. So we can just say for input in layout sorted by offset do fields.get index, and we have the field for that. So we could just say, yeah, let's say this is a list. Easier. And then we can say fields sorted by index dot push that field name. Okay, yeah, and then in the end we just return the final thing. Oh yeah, no, this is not that. This is a struct layout with field to offset, field to layout, and fields sorted by index. Yeah. This is clean, I think. There were no, yeah, I know. Key is not a field on string. True. Very true. Okay, field to offset. And up here. So let's list. Oh yeah, these are all. Yeah, I guess. Yeah, this is a list. So this should be converted to a slice, like this. Okay, next enums. That will be pretty similar, I think. Yeah, okay, so I think what we're gonna do is, yeah, payload size is 0, payload alignment is 1. Then we have variants, and this will be, in the end, this will just be this, variant layouts, map from string to variant layout. Beautiful. And then here we have for each variant in the enum, we have the type. Yeah. Oh, we layout. Yeah, we layout that. Layout the args. List of memory layout here, and for each arg and variant value, we do this. Oh yeah. Yeah, I mean, why did I copy that up here? This is basically what we do down there. This is exactly what we do down there, which is a good sign. And we're just gonna call this layout instead of efficient layout. Okay. Okay, I'll lay out the args. Boom, we do that. Then calculate derived info, which means we need this for each arg. We have the arg offsets here. List of string. Okay. And that's basically what we have down here, right? This tells us input to offset, and the inputs are directly the args. And we also have inputs sorted by offsets, which is args sorted by offsets. And this is already, yeah, okay. Well, that's simple. Nothing to calculate here, really. So yeah, we just update those. Okay, this is interesting. So here we just put the variant layout, and there we have these things, arg offsets. We already have those. That is layout dot input to offset. We need arg layouts. We have those. And finally we need args sorted by index, which is just layout. Input sorted by offset. Yeah, args sorted by index doesn't make any sense. Args sorted by offset. And same here. Yeah, then we have variance.push, beautiful. Yeah, and then we have the tag size. And tag offset is payload size. Yeah, the tag is the last thing. So this is that. Yeah, alignment is payload alignment. Then we have this kind. Oh yeah, that's the enum layout, including the tag offset and the tag size and the variance. Beautiful. Okay, ooh, that was some work, but now we have these very, very descriptive and easy to work with memory layouts, where we basically have all the information. We have the fields sorted by offsets. We can, given a name, we can get to the offset, to the layout. We know that the size of the tag of the enum, we don't have to recalculate that somewhere. All of the logic can be in one central place. Okay, so to go over args in the layout order, not the semantic order. So basically we want to, well, that doesn't help us here. Damn it. Yeah, okay, it does have this. So we can just say for input arg, I don't know, and layout, but inputs sorted by offset, do stack model find distance from top of this arg. Call that arg. Yeah, let's maybe call this input copy them. Let's maybe unindent that. Okay, layout arguments. Yeah, copy them from further back on the stack to here. So yeah, we have arguments, and then we stack model find distance from top of the argument is just call the args get input because that's the index. Yeah. Then we get the distance of that from the top. And then, well, we want to push that. So maybe call this copy from stack or something. And maybe also, I think it makes sense to have instructions as the first thing, because the other instructions, you know, we also just call push and so on. Yeah, copy from stack, and then, you know what, let's just put the offset and the size in there. Because why not? Yeah, and then for each byte in 0 to size, we push that. Seems fair to me. So then in here we can say instructions copy from stack and the offset, which is this, and the size, which will be arg dot arg dot input maybe. I am not sure. And basically the type of that, right? Yeah, layout is arg layouts get input. Let's call it index maybe. Yeah, the size is the layout size. That's the important bit. Okay, so this call, yeah, okay, that works. And then we say stack model dot yeah, we basically want to add padding. Ooh, how do we do that? layouts.get. I have no idea how that's gonna work. Instructions.copy from stack. We don't need to add mappings for that. Yeah, this. Okay, so we need to add padding. And also then make the model consistent with that. Ooh. Do we want to have some sort of, I don't know, builder or something that wraps the stack model and the instructions list, and then instead of passing both of these around in here, instructions and stack model, or only passing around the instructions and then having to yeah, and only then having to adjust the stack model afterwards. What if, yeah, this should, for example, do this, instead of having to duplicate this, when we copy some things to the stack, or we align the stack, by the way, we also need to this is really easy to forget that you always need to add instructions that do something, and then also apply that to the stack model. So I'm proposing that I'm unifying this to some sort of builder, which is only used within a single function. We don't need the stack model, it's created here. So I think it's fine if we just, we could just rename the stack model. Oh, I like that. Let's move the stack model down here, maybe. Call it bytecode builder. I don't know. Stack model mapping. Yeah, I don't know. Let's maybe add an extra struct for that. So bytecode builder. Yeah, where we basically just have a stack model. Good. Yeah, we could inline them. Stack mapping. Yeah, let's do that. And instructions, which will be immutable reference to the bytecode instructions list. And then in here, instead of this, we just have a builder. Okay, yeah, and this is every builder is that. Every builder mapping is actually the stack mapping, and the builder size is the builder stack size. Okay, yeah, that makes sense. Okay, so we have these simple helpers first, hey, just add mapping. and find the distance. Like this is the mapping stuff basically. But then also align something to this alignment. And that would basically mean that we emit instructions as well. So builder dot instructions dot push. Like this should be the new size, new size. And then for if in new size to our actual size, like builder stack size, we need to push an instruction. Bytecode instruction. I will push 0 padding there. Why not? Or push something we can easily recognize, like AA, which I think is the typical thing for uninitialized memory. So then we have builder.stack size is new size in the end. Yeah, that seems like it makes sense. Oh, crazy idea. We can even go a step further. Not a stack further, but a step further. And it does make sense to emit, basically to have a function for each of these, and then that function just automatically updates the stack model. Maybe that makes sense. Yeah, I think that makes sense. Sure, let's add functions in here for every instruction. And it should return nothing. Yeah, like that. And a push 8 just takes byte. And now just two things. It pushes the instruction, like builder instructions dot push bytecode instruction dot push 8 of that byte, and then it adjusts the stack size. Hell yeah. 1 byte. Okay, and this will take some time. And let's maybe add, in order to make it easy to generate bytecode, and for this to not get out of sync with our content model of the stack, we have a bytecode. Yeah, each instruction you can emit is available. Each instruction has a corresponding function that appends the instruction to the array, I guess, to the list. The instruction buffer, and also adjusts the stack model, and also updates the stack model. Yeah. Okay. So here we have this call doesn't work. This is the signature push. Int. Yeah, I mean an alternative idea, which I think is a bit more sane, would be to have a single function on instructions that tells us the amount that it changes the stack size diff of an instruction. We could call it that. Yeah. And we put that in here where we actually need that. Yeah, so then we could have some push function or emit function that just takes an instruction, which is a bytecode instruction, and it pushes that instruction to the instruction buffer and then adjusts the stack size. So builder stack size is builder stack size plus instruction dot stack size diff, and that is defined down here, where we basically go over all instructions. Oh, come on. Nice. Oh no, that was used the pattern in. Yeah, just deleted. Oh no. Yeah, this looks bad. Yeah, not all of these comments containing nothing is bad. Okay. So we switch on things. Yeah, this pushes a single byte. This pushes 8 bytes. This pushes a single byte, this pushes 8 bytes. This well, this takes a skip and a mount. It takes, yeah, it tops the amount. So there are there's no unary minus. Yeah, so it's just that. This does nothing to the stack. Cool. Jump table, I don't know. I guess. Oh. Call. It depends. Yeah. Return instruction. Okay, it doesn't really make sense in every case, to be honest. Yeah. This is -8. Because they consume 2 ints and produce only 1 int. Yeah, Menel, oh, that's interesting. Yeah, Menel consumes a a size which is 8 bytes, and it consumes an alignment which is 1 byte, and it pushes the size again. So 1 byte minus, storing, oh, that's interesting. Consumes 9 bytes. This consumes 16 bytes. This consumes 8 bytes, but produces 1 byte, so load does nothing. Yeah, and crash, I don't know. Okay. Yeah, and then we don't have this. Yeah, we do have an align to, which really is just an alignment, okay. Yeah, and then for each of these, this doesn't make any sense. Smaller actual size should be there. To new size, do builder dot emit byte code instruction push 8. Beautiful. It's a byte. Oh yeah. And then we say builder.stack size. And we don't need that because the emit things already do that. When we do push 8, we immediately also adjust the stack model accordingly. That is nice. Okay, yeah, let's maybe turn this into a constant, because why not? Padding byte equals that. And then in here we can just say padding byte. Beautiful. Okay. Yeah, so the copy from stack, that is down here. And what we actually do is I'm gonna put the helpers up here because they're all, cozy together, and okay. So align to does the correct thing, I suppose. Yeah, copy to stack. Also, yeah. Yeah, this should take a builder. Yeah, offset and size, and it just does builder dot emit this instruction. Beautiful. And then we have, let's call it comp time, like create value, maybe. And again, it pushes the instructions to the builder. It makes total sense. Yeah, instead of these, we just have builder.emit. And these also automatically adjust the stack model, which it didn't currently, because that's easy to forget. Yeah, I guess comp time value or something, or what it was called. Uninitialized means, oh, we could say push padding or something. count for 0 to amount, we basically push the padding. Beautiful. And then the padding is the this minus the actual stack size. Yeah. Oh yeah, emit padding maybe. And yeah, we'll just take the what? Yeah, something like that. Hang on. Crazy. Crazy. Okay. Yeah. Like really simple functions if you really get down to it. Yeah, this would just be builder.emit padding layout.size. Amazing. Oh yeah, this should be a builder. Like that. Function using that builder, beautiful. Yeah, we should be able to say builder.align_to, and that will emit padding, padding instructions, and also like adjust the stack model. Okay, yeah, and then we have builder.addMapping. Yeah, sure. Never know, what's it called? ToValue on create value. Emit value would also be nice. Like push value. And for this as well, because we don't, we actually do push something here. Unlike the just instruction thing where we emit something and it may push something, may pop something, pushing is the more specific thing that we do there. Yeah, here we can just say builder.copy from stack. From where? Well, no way. I think we can just, oh yeah, this should, we don't need to do that. Because the copy instructions already push that. And here we just say builder.align_to, beautiful. I think we just copy from stack. And copy from stack is, yeah. Let's add another one that just takes an ID and a size, yeah. And it no, hang on. Oh yeah, it just calls copy from stack of builder.find difference from top. Yeah, this. Yeah, so now you can actually just say, hey, please copy the argument. It's somewhere on the stack. Please copy that. Good. To put a reference to the function in the builder as well, and then we could get the size of the using this, you know. Would be pretty amazing. Damn, that is so cool. Yeah, I don't know. For now, I'll leave it like that, and then. Okay, so this emits a call instruction, and oh yeah, here we need to patch the builder stack model size explicitly. So patches.push. Patches.push. Yeah. That will just be builder dot instruction get ref builder dot instructions dot blah 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 blah. Yeah. Yes. Ah, yeah, and then we need to call dot receiver return type dot memory layout dot size builder dot stack size minus layout. Builder.stack size minus builder.layout. Yeah. Dot something. Builder like layout dot size, just the layout of the arguments. Yeah, return type is not a field on the signature. True. So we need to get the correct type. So you're good. Dot funds, and then get that probably. And then get the function's return type, memory layout that, get the corresponding size. And Yogurt is not a thing, exactly. So we have, before we didn't need that, but now we do. Oh yes, we do. Yeah. So I think we need the yogurt. has these. Yeah, okay. So the fun is yogurt. Funds, we call the receiver, and then we can say fun. No, hang on. No. I'm gonna leave that inline down there. But I'm gonna add a return type function to the yogurt. So on, let's say up here. You can write these things. Beautiful. And you can also get the return type of the fun, which will be a fun type, and which will just get the fun expressions. It will get, how we can just say fun.get, yeah, of fun.body.returns, not sure. Yeah, that's a yogurt expression, and that has a type. Nice. This is pretty cool. Yeah. Okay. Yeah, instructions. This will just be builder.emit. Oh yeah, this will be not a stack builder, but a builder with a stack mapping, I guess. Get name, by the way. Stack size and instructions. Okay, nice. Yeah. Here we can just go over the body parameters. And this is like param.item, and this is layout.input to offset of param.index. Oh yeah. Okay. Then down here we say will a compiler and needs the yogurt. Which means that this thing also needs the yogurt. Which means that this thing also needs the yogurt. Okay. Compile yogurt body. Oh yeah, bytecode builder. Yeah. Oh yeah, we don't need the instructions down here because they're inside of the builder. That makes sense. Push value. Okay, yeah. You know what? That's it compiled. That's at least something. So let's maybe okay. We create lambdas and this crazy stuff. Let's just say we add 2 and 3 and see what happens. Function post angle. Oh yes. Okay, so we've emitted instructions for the function. And I think the next step would be to push the return instruction. And now there's a simple way to do that. Copy from stack of this and its type. Well, the type being fun.get body return. Oh, hang on, fun.return type. Oh no, maybe a different body. Fun.get returns.type. Oh, yeah, we need to lay out that. The memory layout dot size. Okay, we have that. Next would be pushing instructions, like popping the other instructions. So builder dot emit bytecode instruction pop below top. And yeah, how many do we want to skip? Okay, makes sense to save this. Return. What size is that? And then all of the locals should be popped. So this is, oh no, hang on, all of the body, yeah, maybe stack size add body start is builder.stack size. And then in here we can say space of locals. Yeah, size of all args and locals. Yeah, I don't know, size of args and locals is builder.stack size minus stack size at body start. Nice. What do we do here? We push n below top. Params.len plus body expressions.len. Oh, okay, so I think one of this was, some of these were commented out before. Probably. Yeah, and this will just be bytecode instruction dot return, ret for return. Okay. Beautiful, somehow, I think, maybe. mean, yeah, it was compiled to bytecode, so that's something. But let's actually look at the bytecode, you know. Yeah, hang on. That is the bytecode. Yeah, it can contain weird pointer stuff. So if there's just garbage there, we may not want to print that. Yeah, you know what? Let's maybe try to print that at least. Let's say bytecode is this, bytecode, and then I don't know, 50. We do the following. We take main, which is an address, and we say, okay, let's take main plus the size of one bytecode instruction multiplied times I. And then let's print that address, the pipe, and then the instruction there. So address dot to reference bytecode instruction and dereference, and put that to standard out immediately without aggregating it into a string and then sending it off, so that even if this fails, then we still have the address. That's basically it. Oh, and yeah, no, we do print new lines anyways. And here's one. Let's just see what happens. This will crash somehow. This will, I'm expecting a segmentation fault after some instructions, but okay, what's going on here? Push object. Oh, we can't even print the new instructions. As this is sad, honestly. Oh yeah, this makes no sense at all. So there is a push 8 instruction with a byte. There is a push 64 instruction with an int. There is push 8 from stack. Offset push 8 from stack. And same with this. Then there is pop below top. There's a jump to a target, a jump table, which jump to, and then for each entry in the table, hang on, jump table, and this is just jump. And the entries will not print any new lines, it will just be the, the targets. With a space in front. That makes sense. Okay, struct doesn't exist. Member doesn't know. These are like high level things. No. So let's just copy these up here, and jump table is what we have. Call, and I'm not calling it kind of weird. So let's put all of them in here. Print cases, and then just print them. For a lambda call, there needs to be a target. I'm not even sure what that is. Call red. And the cool thing is that most of these don't take any arguments. None of these take any arguments. That is pretty cool. Okay. It compiles. Whoa. Okay, I did not expect that all of this is like these are valid instructions. Dang. Okay. Okay, that is wow. Oh, interesting. Interesting. It does not look right. So how? Wait, what's going on here? Yeah, but maybe when emitting instructions also print something. Yeah, and let's just print emitting instruction. Emitting push 8 2, emitting push 8 3. Why though push 8? Is the printing is correct, right? Nope, it's not. Oh, of course it's not. Oh man. Yeah, that looks better. Okay, so we have constants like 2 and 3, and then some things for some reason. And then we emit a call. Yeah, that seems correct. Except like that this doesn't make any sense. Push 18, oh wait, 16 is that. Push 8 from stack. Oh, is that A? Is this hexadecimal? I'm not sure. Push, no, this is not, this is just byte. I'll get it. Yeah, maybe let's, in the emit code, let's do something like if instruction is push 8, then panic, and see where this is called from. It is never called. Okay, oh, because it's push 8 from stack. And it just doesn't print here correctly. I see. Oh, so we copy some things somewhere. Oh yeah, it does make sense. It does make sense, okay. Yeah, so let's maybe just fix the instruction part printing. What? Why? Okay. I'm not gonna question that. Yeah, let's just look at this, you know. So this seems fine, first of all. And then we want to call the plus function, which means that we push the arguments to the plus function, which are 16 bytes. Yay. Yeah, maybe that's in the copy thing, you know. Copy from stack, yeah, and the size. Beautiful. So maybe let's push some 64 thing from the stack. I think it has to be that. And here -1. Yeah. So if the size is smaller than 8, then we just break. Else we do that. Pretty simple. So as long as we can copy 8 bytes at once, we just copy 8 bytes. Otherwise, for the rest of the bytes, we just copy them individually. Okay. Oh no. Oh yeah. I see. Yeah. So this right here. This is kind of like a while loop, you know? Nice syntax construct. Loop if size smaller 8, then break, else. Yeah. And here we do that, and we also set size to size -8. Yeah, I'm just gonna ignore this because there is something in there. Oh yeah, but this looks much cleaner. Ooh, yeah, so we push a 2, then we push a 3, then we push not the thing at offset 0, which would be the 3, but we push the 2 at offset 8. And then we push the thing at offset 8, which is now the 3. So we've pushed the 2 and the 3 again on the stack. Then we call something. And yeah. Oh yeah, calling consumes these 2 and pushes a 5. But here we have a separate expression for the 5. It's just that we have this thing which is like never used again. And that's totally fine, by the way. So what we do here is we push this, we push this to call this, yeah, and then we just ignore the result. And we push a 5. And then we push that 5 again, because we want to return that. Yeah, and then we push, we pop, we keep the top 8 bytes, which is the 5 that we've just duplicated. And we move 40 bytes below that, so 5 ints, basically. And that would be this 5. That would be the result of the call, which would have consumed these ones. It will be the 3, the 2, and the argument that was passed to main, which was expected to be on the stack. So all of these 5 are popped. So after we return from main, the only thing that remains is a 5 on the stack. That seems correct. Okay, and now things get weird. Now we have these weird things here. Okay, so apparently I think maybe some things are shifted. Do we not get the correct? We take I times, oh yeah, here we need the sprite size of, yep, in Rust this wouldn't have happened, because in Rust there is no concept of this. Okay, oh yeah, this looks correct. Nice. Nice. Okay, so we have a call, and apparently there's, when printing a call, we don't actually, no, we don't print anything. Why? Call target, and target will just be, you know, machine code, like an address of where more bytecode will be. Hopefully. Oh, look at this. Oh, look at this. We push a 2 to the stack, we push a 3. Then we copy both of them again, and we call this EC478. 478, that is down here. You know, after the main function, we have another function apparently. Crazy. Yeah, what does that do? Oh, this does not look correct. Ooh. No. Okay, what does it do? It should, in theory, add 2 numbers. And it calls 520 for that, which is this function right here. Oh yes, this looks correct, kind of correct, because this is this function called built-in add. Yeah, it's this function, which just, you know, it does a comp time 5 push 5, and then it duplicates that 5, so it's 2 times on the stack, and then keeping the top 8 bytes, aka the newest 5, and removing the 5 below, and it then returns. So it just puts a 5 on the stack. It puts a 5 on the stack, and apparently the arguments, because they are comp time known, they don't take any space on the stack. That is interesting. I did not know that we do that. Okay, so this is the actual add function, which will, I mean, it should call this other add function, which makes sense. And then it ignores the result and just pushes 5. And pushes that 5 again, and, you know, pops some things. And it also doesn't, like, it pops 3 ints. You know, keeping this int, it would then pop this one, the result of the call function, is 2, and a third one. I'm not sure which one though. Well, okay. Interesting. So I think I'm really not sure what's going on here. Like the push, it seems correct. Push 64 from stack. -8. -8. Okay, so offset is 0 apparently. Which can, oh no, sorry, this is, I mean, it would make sense, you know, if this is 0, but size is 8, for example. You know, if size is bigger than the offset, then something is wrong. Copy from stack with offset, but size. I hope this will trigger. Yes. Offset 0, but size 8. Really? Hang on, where is it called? Copy from stack. Copy from stack, yeah, compile yogurt body. I'm not sure. I did want to refactor the comp time thing anyway. You know, for now, let's just say that the comp time calls, like, where's that? Plum? No. And the yogurt. Yeah. If you call something, then, you know, if all of the parameters are comp time parameters. Yeah, this right here. Yeah, then we also want to basically call the function at comp time. Otherwise not. So, okay, we have the name, we have the arguments, we have the argument parameters, we have all args comp time. This initializes the argument parameters. Yeah, this is just args.push. So args is a list of yogurt IDs, but what is call then if not yogurt IDs? Interesting. Call.args. And I'm just gonna say builder get arg is comp time. If that's not the case, okay, so arg is an egg ID. Oh yeah, that makes sense, I think. Okay, you know what, let's first map the arguments to yogurt IDs. Let's split this loop up. Args dot push compiler dot lookup arg, like this. Then we have the arguments, so we don't need to do all of that at once. Then we can check are all of the arguments comp time by just iterating over the args, which by the way we can convert to a slice right up here. Beautiful. Yeah, and we can check is this your expression.op, I think. Yeah, if that is not comp time, then they are not all comp time. Beautiful. And then here we can go over the arguments again. We can get the type. We don't need to do this. And instead, we can just say, instead of doing this, we say if are all args comp time, then we do that. Well, yeah, I'm gonna have an if and an if, because why not? Again, this is not super clean, it's just something to get this working. But I think that, like, from a rough design perspective, like, this is useful. Should be cleaned up, definitely, but these kind of abstractions, they settle over time. So called copy from stack with offset 0 with size 8 still. Interesting. Is the yogurt something else now? Not really. Not really. Okay. Interesting. I would have thought that... Oh yeah, because they are all comp time known. That makes sense. How about if false? Do everything at runtime. We have no comp time parameters. Yeah. Doesn't work with type reflection and so on, but should. Yeah, okay. This is actually what I want to lower for the, for this one. It's a bit simpler. So we have a main with an int. Okay, we push 2 and 3. Makes sense. And then we call something. Okay. Next function plus. Yeah, just takes int and int. Very nice. So apparently it doesn't get initialized correctly. The parameters. Well, we have the param layouts. Then for each parameter, we add the its memory layout. We compute that, add that. Yeah, we compute the memory layout. I'll repeat it. Well, yeah. And then we add a mapping from the body.params from the item, which will be the yogurt ID, to I mean, we could also say builder dot stack size or something. Oh yeah, we should actually add stuff to the builder here. Yeah, that makes sense. So we add mapping. Efficiently. Oh, no. I think we should go over the arguments in the order that they were layouted. Or even simpler, we just do this. And then we say builder dot, I don't even know, builder dot, I think the align should happen before the arguments. Yeah. So builder, and in our case, like the stack model is empty, so aligning the 0 to 8 doesn't make any difference. So builder dot stack size, yeah, is initially just the length of the parameters. So layout dot size, yeah, that makes sense. Yeah, let's try this. Okay, yeah. Yeah, before we just had a comp time value. Now we actually want to emit an add instruction. That makes sense. So we push 2 and 3, then we push the arguments to the call. So we push them again and call something. Okay, and inside of the call, we push the arguments again. Which I'm not, this should not be, I mean, after we've pushed something. I mean, I don't know what's going on here, so it may as well be correct. Okay, and then the important thing is there's an instruction that we want to do. Yeah. This now should be possible. So for each of the arguments, we just push that to the builder. Yeah, so builder builder copy from stack. Yeah. The argument, which will be some ID, and also we needed the type of the argument. So fun dot get arg, I think, dot type dot memory layout dot size, something like this. Actually push the arguments to the stack, and then we push some instruction. That makes sense. The arguments are automatically popped by emitting the instruction, and other arguments are pushed, and so on. So that's beautiful. Ooh, it compiles again. Let's see, this looks like the add function. Oh yes. So on the stack we should have 2 arguments. And then we push the first argument, that's on the top of the stack, we push that again. And then again. That does not seem correct. We add something. We push something that is like way, like somewhere deep in the stack. Like what's going on here? What is going on here? Let's maybe params, yeah, this kind of thing. Let's print the mapping. param mapping is builder dot stack mapping. Oh yeah, probably we need to debug print it. Maybe not. Okay, apparently not. Kind of afraid what's gonna be up here. Oh. Okay, yeah, that makes sense. Oh, yeah, that does not make sense. They should not both be at position 0. Add mapping this to layout dot input to offset of the index. Okay, so the layouting doesn't work correctly. Input to offset. So initially the offset is 0. We put we round that up. Okay. We say the total size. We add that. Oh, I see. We don't need size and offset. We just have an offset and an alignment. And first we see, hey, where do we want to place that? Boom, then we place that there. So now the offset for the next iteration, for the next field, next input, is that plus the layout of the item dot size. And then in the end, the offset is just the size. Because it's basically where would we add the next item. And that's after the input. Okay. But that's actually like a useful error, you know. Yeah, this looks better. Like it still looks weird. And I think this function is not correct. So it pushes, like this is the add function. It expects, like this one, it expects 2 arguments, 2 integers, to be there on the stack. So what it does is it pushes the thing that's further back on the stack. The first argument, the first int, then it pushes the second int, which is now that the stack moved ahead 8 bytes. It's like still 8 bytes behind. Okay, and then it calls this other add function. I mean, totally fair. Then it pushes that function's result to the stack again and pops some items below the stack. 8 in particular. Oh, that's not enough, is it? Because here we have 2 arguments on the stack already. We duplicate them, so now we have 4 ints on the stack. But then we call the add function, which consumes 2 of them and pushes the result. So now we have 3. We push that again, so now we have 4 again. And we should pop like 24 of them. Okay, let's see. Function post and will no longer exist. Well, that kind of, I like that. I'm gonna add a comment down there. Man. Nice. So, size of args and locals is the builder.stack size minus the stack size at the body start. Stack size, yeah, that makes sense. Oh, does it though? Does it? No. Because here we expect that the parameters are already there. Size of locals is this. size of arcs is something, you know, it's completely different. Oh, which will be the arguments of the body and oh shit. So this will basically be, and what's the call? This. Yeah, this. The total size of that. Oh man. Yeah, I mean, okay. Let's just copy paste that in here. It's not clean, but at least it works. So arg, let's call it size of params, because we're looking at this from the point of view of from inside. Yeah, param layouts are these, and then we have body params, where we push the param memory layout. Okay, in the end we have a layout. Nice, and that layout has a size. Beautiful, beautiful. Yeah, size of params plus size of locals. That makes sense. Yeah. By the way, we're memory layouting things all over the place. We probably want to cache things there, especially if we have some more computationally expensive memory layouting strategy, like actually like rearranging the struct fields and so on. Yeah, but for now this seems to work. So okay, we push the two arguments, we call the other function. Yeah, we have two arguments, we push two arguments, we call the other function which pops two and pushes the result. And then we push yet another one, and then we pop three of them. Yes, with the top one remaining, so these three. Okay, and then we return that one. Perfect. Okay, for the outer function, we push two, we push three. We already have the argument to the main function on the stack. Then we push two, we push the number three, we push the two again, we push the three again. We call this other function which pops two and pushes one. We push the result, and then we push 32, which are 4 8s, leaving only the result. Wonderful. And finally, the built-in, you know, this one, the built-in add function. Yeah, this one. Yeah, two things are on the stack, and then pushes them again and again. Adds them together. Beautiful. And then pushes something from the stack that's like far back. Why? Why? I mean, even for instructions, you know, at the beginning of this switch, before that we still add a mapping to the stack size. Yeah, that makes sense. So actually the result of the add instruction should have a slot on the stack somewhere. And then when pushing that at the end, down here, we should find that mapping. Where? Yeah, here. Yeah, this should work. found value size, is that correct? Maybe? I'm not sure. Oh yeah, it's the same that's being passed here, which is 8. That's correct. So what are your returns? Builder of mapping. I'm just going to print that, you know. Mapping is builder of mapping. Somehow like this. Well, mapping is not a field here. Oh yeah, because that's distinct mapping. Okay, we have the add instruction, and then we're done. So yeah, instruction 0 is at offset 0, makes sense. Instruction 1, sorry, int 1 is at 8, and expression 2 is at offset 16. That is correct. That's very correct. Then the size, maybe size and builder dot stack size. What is that? Oh no, that's that's a bit generous. So where's the stack size? Even where's that affected? Up here for call. Yeah, which we don't have before that. What about the add instruction? This is, oh, negative numbers don't work. Oh no, hang on. Let me check something. Print -5. But I have used negative numbers. What? What is going on here? Oh, I can imagine where the bug is in the Martinaise compiler. Let's maybe open the compiler and fix that. So we can have negative numbers. That's so in the Martinaise compiler. I don't want to give a complete introduction, but basically it's similar. We have a couple of stages, we pass things, we monomorphize things, and in the end we have these soil instructions, which are defined somewhere. Yeah, very similar, but more, they are register based. So for example, we have move instructions, yeah, that take a register and another register, or move I, which takes a register where to put something and a number. And these registers, they are defined somewhere. Yeah, so there are these registers of the virtual machine. Right. And when I emit these instructions, some of them are, I try to be smart sometimes, which is probably my downfall. So the way I do that is I have this assembly struct, which contains a soil thing. And you can see that here. So I have a couple of functions, a function for each instruction, which then emits an instruction to that, basically adding it to a list similar to what we do. But in order to be smart, I have some, like smart instruction, fun, smart, yeah, these. So for example, when moving a value into a register, I check, hey, is this value maybe in the range from 0 to 256? If so, then I use the move IB instruction, which moves an immediate byte into some register. Otherwise, I use the move immediate instruction. And this one right here, move immediate byte, the idea is that when instructions are encoded, it's not actually this enum, but later on they become like a very dense binary representation. Yeah, right here. So you can see that every instruction, like move I, for example, just becomes the byte D1 followed by some other stuff. And move IB becomes D2 followed by other stuff. And it makes sense to choose shorter instructions when possible. Yeah, that's the entire idea. And apparently, okay, I was thinking maybe like the choosing of the smart instruction was kind of broken. Yeah, so what do we have? We have these three. Okay, this is probably not it. This is just, I want to add some value to some other register. And because there is no add immediate instruction to basically taking a register and an immediate value, you first have to put that value into another register and then add that to the first one. But of course you only have to do that if the value is not 0. So this just checks, is the value 0? If so, then we do nothing. Otherwise, we move the value into some temporary scratch register, is what it's called. And then we add that register to the actual target. Okay, and yeah, smart move and add offset again. Basically we want to move from this register to that, but also add an offset and not use an extra register for that. So the way we can do that is if the offset is 0, then we just directly move that, this to that. Otherwise, we move the offset into the to register and then we add the from register to the to register. Yeah, the destination is always on the left. It's kind of weird. Okay, and I was thinking maybe the error is here somewhere. Like for example, we only check if immediate is smaller than 256, and then we choose this one. But that's not the case actually. So kind of stumped by that. Let's maybe, let's do something. Let's comment out everything else at least. Only print -5. Okay. So we have something that's easily reproducible, and we can print the ast of that. Well, to be honest, I wouldn't have thought that this results in a Martinaise debugging session. And let's look at the mono that only contains the necessary functions. Yeah, so printing is complicated. Printing of numbers. Okay, so here we have the functions. There's an exit function, which is implemented directly in assembly. A write function for writing some radix on. Sure. Let me move out a bit. Yeah, printing some things, writing them. Okay, writing, printing, more printing. Here's the main function. And this is correct. The int is -5. And then we call something, we call printline with that. Fair enough. Okay. Then last stage, I think the soil. Yeah, the actual instructions. Which means we kind of have to look for the main function, which is somewhere in here. But we can see that there is a lot of setup stuff. Then in the end we call instruction 950, which is down here. Hang on, 950, yeah, and we can see that this is where main begins. Okay, so we do some stuff. Oh, I see. Yeah, we call println hello, like welcome to the something compiler, Plum compiler. Yeah, I see that. I'm not actually sure what we do here, but sure. Yeah, then we print that. Oh yeah, and then we want to print hello world. Print the -5. Okay, so in the beginning of the function, those constant variables, they get initialized. Oh, and we can see that here's, you move I, b -5. And then restore that somewhere. That looks correct. That's perfect. Move I. Okay. Hang on. Let me maybe compile this to plum.soil. Okay. Now let me run this with another compiler. Like this. Okay, same result. That's at least same. That is. I'm a bit stumped why that happens. Okay, so maybe let's look at the next and last stage, which would be to turn that thing, that soil, into a binary. When emitting a register and an int, we call this emit with an int, which may be negative. So far so good. Yeah, this doesn't make sense. This should be int. Oh, yeah, we emit byte. Yeah, that makes sense. Oh yeah, emit byte, but it takes an int because it's just painful to always write .lower bytes somewhere. But we do have emit with an int somewhere. The question's just where. bin.emit fun emit. Yeah, emit instructions, emitting a byte. Oh yeah, here. I see. Is this not correct, maybe? Maybe it's not. Oh. I think this is not correct. Hang on, let me maybe take this Yeah, this is not correct. Because for a negative number, we should have the least significant byte. For the -5, that's, like 251 or what it was. But then, in order to indicate that this is negative, all of the other bytes should be FF. But in this case, because the int is quite small, like -5, dividing that by something huge is 0, and then ending this with 0 is 0 again. I think this is actually, this is incorrect. How do I fix that? I could maybe try to, like, a special case and like check, hey, is this negative? Then if the division results in 0, I choose something, but that doesn't seem like a correct thing to do. Hang on, this, like, ints are always guaranteed to be little ending. Can we just, oh yeah, I think I'll just iterate over the bytes. So I'm going to take this int, the word. I'm going to take a reference to that. So now I have a pointer to that int in memory. I'm going to cast that reference to a reference to bytes. Yeah. And then I do that. I emit those bytes. So rather than calculating something, I directly reinterpret that memory into... Oh yeah. So this still needs a pointer to int, casting that to a pointer of byte. And this is not correct because... Oh yeah, because these are not like this. Oh yeah, you can't iterate over an end byte. You can only iterate over slices, for example. So let's maybe add a slice. Like... We know that an int has 8 bytes. Like this. Some byte. Oh, it's just address. Okay, that's, yeah, we don't even need to cast anything. Just convert that reference to an untyped address, and then we have that. Why is that slice of byte? Emit, oh yeah, I can just do emit with the byte. Oh, that's also nice. Yeah, and I probably want to do something similar here. Like, we take the bytes, and then for 0, for I guess in 0 to 8, we do something like this. Bin.bytes.get ref post plus I equals, well, the corresponding byte. So bytes get I. And that's even cleaner code. I think maybe it is kind of cursed, you know, to do that. It's definitely unsafe. But Martinaise is not a memory safe language. That's fine. Right. So let's maybe let's maybe rerun, like rebuild the Martinaise compiler first. And then I'm gonna get some more tea. And then let's just run that. Haha, okay. Yeah, this is much better. Okay, we can have negative numbers. Negative. How did that never occur before that? Is crazy. I don't know. I really don't know. Okay, so we have some instructions, and yeah, this looks a lot more reasonable. No 250 ingot. So we have the main function, calling the plus function, calling the built-in plus function. Oh, hell yeah. Which accepts argument number 1, argument number 2, and then pushes those two, adds them, pushes the result, and pops the first 3. Perfect. Okay, and the rest is just garbage being just chilling here. That's fine. Okay, so compiler to bytecode. That is neat. That's really neat. That means that we can now run this, right? Yeah, not like this, because that's but somehow kind of like this. We did this before. I think we can do that. Results bytecode. Let's say main. That's an address, right? Yeah, we call that, and we expect something here. We expect 8 bytes to be precise. So we need to have some bytes in here. Oh, hang on, we can just say filled slice. I think filled slice of bytes. I think it takes the length and it takes a byte, which will be so. Yeah, so we call main with 0. That returns an int, which we then print. Okay, so we have, so we have this, the data stack. It looks fantastic. Oh, yeah, it doesn't return a reference. No, it just returns result data. That's a slice, right? Yeah, a slice. The data, return that to a reference to an int, and then we dereference that. Makes sense. We add 2 and 3 into 5. Nice. Very, very nice. Using this code. Nice. Okay, I don't want to do like too long today. I'm just happy we got something working, because this is like quite a huge step we took from this high level, let's just have objects anywhere, to now calculating custom memory layouts and pushing bytes on a stack, and like having everything on the stack, and having everything like doing all of the memory management ourselves, basically. That is quite cool. Yeah. Okay, I think next, let me first commit this. Okay, so a few things. Remove deprecated C in the backend. Then we have memory layouting. We have this crazy thing. We have this, and we can write instructions, and we fix some things. Oh, yeah, this is kind of separate, actually. Yeah, let's just commit that. Yeah, like don't specialize functions for temp time args, all at runtime. Okay. Implement a low-level VM. Oh, get that somewhere. Yeah, make VM low level, and now we some parts of the low-level VM. Beautiful. Yeah, the soil file we created, we can just remove that. Just like the test and the bin and the C. Oh, I kind of like that. Oh yeah, we did some things here. Sure, let's commit that. Like, especially this is useful. Yeah. Sure. Update test file. Nice. Cool. Yeah. I'm gonna take a small break. All right. So let's maybe look at structs next. Yeah, creating a struct. Yeah. Now this should actually be workable. Like, we have to, on a struct in the yogurt, contains something. Oh no, that's the yogurt value. Okay, we got that. Yeah, the yogurt operation. You're creating a struct with a string to yogurt ID. So we already have the correct expressions for the fields. And now the only thing we want to do is put those on the stack and those in the correct order. Right. So I think the first step here would be to to do something. Yeah, we have all the fields. That's fine. And for each field, okay, so we add the fields, and then we need to do memory layouting. So we say builder, we need some copy from stack, yeah, of the value. Okay, it's basically that. Here we get the field, okay, but we want to do this in the order that they are layouted in. So the expression has a type, and if we memory layout that, we get a struct type. And we should be able to copy those items from the struct to the stack. Yeah. Cool. So I guess let's put the struct fields. I don't know. Put the struct fields on the stack. That's basically what we want to do. So we memory layout that, and then we know that the kind of that is a struct. And struct memory layout, yeah, as these kind of things. So there should be a field sorted by offset. So yeah, we should be able to get the field. Let's say offset is 0 in the beginning. Fields are sorted by offset. Yeah. And we get the corresponding field from the struct up here. And we don't even need those, I think. Yeah. Then we want to make some space because of alignment, you know. So field to offset should give us, hang on, maybe let's say struct layout is this. And what we do here is we take the struct layout field to offset. We get the field. This gives us an offset, the offset that we actually want. And yeah, basically for each thing from offset, like the offset we want, let's call that, I don't know, required offset is this. Yeah. And then for the difference between that, now we can just do builder.push padding. Yeah. Required offset minus offset. Then we copy the field from the stack. That's it. And then, oh yeah, we need the size, which is struct layout dot field to layout. So we have a memory layout and then size. Oh yeah, get the field. Get field, and we get that size, and then we set the offset to required offset plus the size of the field. Okay, so we have the value, we have the required offset and the size. And yeah, we push padding. we copy the field value there, and then we go and continue with the next field. That's basically it. And we don't pop anything, like, that's it. Yeah, I think that's enough to support structs. At least creating structs. Accessing members is something else. So yeah, yeah, I guess let's try this out. Let's say we, instead of adding these numbers, we just, I don't know, return 0, and before we turn, we created a point at 2, 3. Okay, so we have some push things, sure, and then push value. Ah, right, because this is comp time now. Yeah, that makes sense. Hang on, what if x is only runtime now? Okay, interesting. That works. So initially we call main 0, so we push the 3, we push the 0. No. Oh yeah, we push the 3, the constant, you know, it's the comp time 3, and then we create a struct with 0 and 1, so the argument to the function and the newly created 3, and that's what happens here. We first push the argument 0, and then we push the 3 to the stack. Perfect. Okay, yeah, and it's gonna be pretty similar actually for comp time known struct rules. I'm just gonna copy this for now and put that, hang on, in this part here. Yeah, so let's say we have a struct x is 2, y is 3. That becomes push 64.2, push 64.3. Pretty easy. Let's maybe remove some part from this. Yeah, and then we have the stack next to that. So 2, 0, 0, 0, and then when the 3 also comes there, we have a 3 afterwards. Beautiful. Yeah, we have the value kind, and it has a type. Yeah, we know that's a struct, and then for each offset, yeah, we don't copy from stack, but instead we basically just want to call push value on that value, right? Because that value is again a comp time known, like a yogurt value. Yeah, we don't need a size for that, just that. Okay, let's see if that works. So let's say I create a struct that is actually a bit more complicated. Oh yeah, this should not have this, and yeah, also don't need this. Okay, let's say I have a struct with x and y and z, and this is just high. And this is comp time known, like this. I don't know what's gonna happen. Whoa. Okay, yeah, so we first push the 0, then a string probably. Yeah, comp times 0, comp times string, then comp times 3. So we push a 0, then string, again consisting of the string pointer and the string length, and then a 3. That is crazy. Yeah, then a comp time struct. And by the way, because these aren't even used, these expressions, so we should be safe to delete them. We just don't do any optimizations right now. Yeah, and we could also delete that, but yeah, okay, so wow. So I guess 230. Huh. We could just, yeah, these are just ignored, and then it pushes those same values again here. And yeah, in the end it returns 0, so it pushes a 0 and then pushes the 0 again, sure, and then pops the things below. Crazy. That is actually crazy. You know, the fact that data structures are not like in the heap, and structs are not a map of some things, but it's just all flat in memory. That's nice. So I guess the next step would be accessing struct fields, like, you know, foo.x. Yeah, this doesn't have a name, so foo equals this, and then we do foo.x, and maybe we even return that. So we need to make members into, alright, because it's comp time now. I see what's happening there. Yeah. Okay, so yeah, this is just a comp times 0. I guess, yeah. So let's maybe instead, is it also comp time known if something else from the struct is only runtime known? Because then that's a runtime struct thing, right? Yeah, okay. So we have something that's a runtime struct. And yeah, so we create a struct, that's fine. And then we try to access that to do member. Yeah, that's basically this part right here. Right. Yeah, we'll do something similar actually. So we know the member.off. Yeah, let's say member.off is an ID, and if we get the corresponding value, or like, alright, hang on, we can get the offset. Yeah, we can say builder dot like get difference between, what was it called? Difference distance, right? Find distance from top. Oh yeah, right, but we also need the struct layout. Yeah, okay. So that's ID, and then we can get the corresponding expression from the function. We can get its type. We know that the type is a struct. So the kind is a struct. Yeah, so we know the layout of the struct, because the type is comp time known, because we have static typing. dot memory layout, of course. Yeah, and we know at what offset the struct is. And because all of the fields of the struct, they are on the stack, you know. So we can just say field offset is, oh, okay, so this is interesting. This is really interesting. I think the struct is the offset is relative to the field to the top of the stack, and I think the find distance from top. Hang on, where does that? How does that even work? Oh yeah, okay. So it returns the beginning of the struct basically. It returns an offset that is the beginning of the struct. And we know the offset of the field in the struct because we know its type. So field offset in struct is, you know, the struct layout dot field to offset of the member name, I think, hopefully. Oh, field to offset, oh yeah, dot get, like that. And now we can calculate the new offset of the struct. Okay, so this would be, because the offset is relative relative to the top of the stack, the offset to the field actually is smaller. Man, because it's somewhere inside of the struct. So field offset from the top of the stack would be the offset of the struct minus the field offset in the struct. Yeah. Yeah, okay. And we also know the field was a type, I think. That's just this. From the struct layout, the field, so the member name dot size. Yeah. And yeah, then we can just push padding for the alignment. And we already do that here. Yeah. And we know the type, the expected type over here. So we can just take type dot size. Yeah, that's simpler. Yeah, but yeah, we don't need push padding. We can just do copy from stack. Type dot size. Nice. Oh yeah, this needs field offset from top. Type dot size. Oh yeah, type has the memory layout. Ah yeah, we don't want to recalculate. Yeah, we recalculate everything. So I don't know. Let's maybe say size is struct layout field get member name dot size. Yeah, this is just the size. Okay. Okay, so we return 0, which is maybe correct. Yeah, this is correct. How about something else? Hell yeah. Okay, let's see what happened here. So we push the struct. Yeah, this is just pushing some int, then pushing a string, then pushing a struct. Yeah, this is pushing a struct, yeah. Because the struct contains 3 fields. It contains 42 at the end. Then the string, which are directly here, so yeah. And then it contains the argument. So this is the struct. And then we access the field of the struct. And because we know where the struct is on the stack, we can then just directly copy, like, you know, push that field. That's crazy. That's actually crazy. Yeah. I can even, like, we may even optimize these, you know. That would be amazing. Like just optimizing these, you know, optimizing these away, and then just pushing things, and that's so cool. Okay, so we have that. Okay. Yeah, I guess let's... What should we do next? Push 64 from stack. Yeah, then we pop the rest, and yeah, nice. We should commit. So this is basically support structs in the VM. Nice. Then, oh yeah, next enums and tags. Switch will be wild, and lambda as well. But we don't have so much to do actually. Crazy. So a tag could just be, let's try that out. I think I have to sneeze. Okay. Yeah, let's say this is sum 5. Yeah, exactly. So, yeah, pushing a value, we need to do that. Yeah, that's up here. And basically something like sum 5 becomes, you know, push the 5 basically. Like the payload, which will push the 5, and then push 8 and the actual tag. Yeah, okay. So I guess, you know, tag dot, what's it, args, something like that. For arg and tag dot args do yeah, we should get the memory layout. I'm just gonna copy that and then adjust that. So we memory layout the type of that tag. The type should be an enum. So this should be an enum layout. Nice. And then for each argument in the enum layout dot, hang on, we know the args layout, like the layout of the arguments. That's just enum layout dot variance dot get, and then tag dot, I don't even know what does the tag have. Your good value tag. Oh, it's a tuple. Okay, yeah. So this has an A. Oh, let's then put that into here. So we know the variant, that's tag.a, and we know the args tag.b. That's a slice of yoked values. Yeah, and here we just take we get the layout of the arguments, and then for each argument in args layout, and it has args sorted by offset. Okay. Yeah, we get the corresponding argument. Like this. Yeah, we know the required offset because that's just args layout. Offset. Arg offsets dot get arg. Like this is just an index, I think. Let's call it index. Yeah, we get the size. That's just args layout. Arg layouts get index dot size. Beautiful. And then we push the required padding to match that, and we push the value. Okay. Yeah. And once we have pushed the payloads of the enum, in this case just the 5, we also need to push more padding, which will be the, what is it? Enum layout dot tag offset minus the offset that we currently have, and then push the tag. Oh, and this depends on the enum actually. So if tag, hang on, if oh, no, this is weird. This is actually weird. Yeah, I think we should instead have something like this, variance and tag, and then we have a tag layout. Which has offset in enum. And that's it. But it only maybe has a tag, because some enums don't have tag, and currently all tags are 1 byte, so yeah, this makes sense, I think. Yeah, so rather than, we should basically check, does the enum layout have a tag? Only then do we push the padding, so tag dot offset in enum minus the offset that we already have, and then we push the tag. So that would be this right here, variant. Oh yeah, and then they don't have any real mapping, I think. think this would just be like type dot, builder dot. I'm not sure. Yeah, I think this would also specify what number means what variant, basically. Yeah, number to variant would just be a string of slice, mapping the number variants. Yeah, kind of like that. But the important thing is that it's ordered. And oh yeah, the other way is also important. Num to variant and variant to num maps a string to an int. So here we have tag.variant to num of our variant. And then we save that. So builder emit bytecode instruction push 8 of that tag. Beautiful. Yeah. Nice. Seems pretty cool. Pretty cool. Yeah, like obviously things in here won't work out. I'm not sure why. Now we get errors in. So the tag field is missing. That is true. That is very, very true. Tag equals, well, if enum dot size is larger 1, so less or equal than 1, then it's none, else it's some. Yeah, and then we need a tag layout. So tag layout contains several things. Yeah, we basically build these two mappings, variant to num and num to variant. This will just be an empty list for now, and this will be a map from string to int. Okay. And then we have offset. An enum field is missing. You need to initialize it with an int. Yeah, we also need to iterate over the variant. So this is basically where we decide what variant is, what variant means what number, So enum, like for variant enum, do num to variant dot push variant. Yeah, let's maybe enumerate them. Yeah. So the item is a map entry and the key is the actual variant. Yeah, and then we have the let's do it without enumerating this. because we like for this one we just implicitly push them, and there was no explicit mapping. So let's say variant to num. Yeah. We put the enum key, the num2 variant.len, and then in num2 variant we put the enum key like this. Yeah. And then in here we have offset enum, that would basically be this, the payload size. You know what, maybe I should do this out here. Probably. Yeah. Okay, so if enum.size is less or equal than 1, and yeah, let's maybe assign that to a variable, I guess. Tag layout is this. Beautiful. Kind of. Yeah. Okay. And then in here, yeah, we can just take the payload. Yeah, if tag layout is sum, then 1 else 0. Yeah, this is kind of hacky, but it's fine, I guess. Like, it's pretty close to this other code, so it's obvious enough. I'm wondering that tag layout doesn't even doesn't show me any errors, but that probably happens. Not, yeah. So num2 variant. Yeah, with both directions here. Beautiful. Okay, so then tag is not in scope because tag is tag layout actually. Well, let's call this tag layout. Yeah, that's cool. Tag layout is some tag, yeah, sure. Okay. Oh, something is still here. Builder limit. Also doesn't work. Oh, okay. Oh, yeah, and it needs a byte. So this is very true. Yeah, variant to num. Okay, let's maybe not map this to an int, but to a byte. Down here. Oh, yeah. Oh yeah, and like string to byte. Sure. Amazing. Okay, I'm not entirely sure what's going on here, but okay, so this pushes a 5. And then other stuff is happening. Okay, so we have a comp time 5 in here. But it's the enum. Oh yeah. This is an enum with only one variant. So only contains the payload 5 actually. Let's make this an enum that contains multiple variants. So let's say, yeah, let's say I have create maybe of a number, and that is just sum a. But this doesn't return sum, but it returns maybe. Let's see what happens. Oh yeah, very true. Oh, amazing. Okay, so we need to switch. That's sure. Yeah, I mean, before even switching, let's maybe look at creating enums with runtime values, which would be, for example, creating the enum, what is it, foo a maybe. Yeah, to do tag. Mm-hmm. Yeah. A tag. So we have a comp time value tag, yogurt value. But what we want now is this right here, which would probably look somewhat similar, to be honest. Creating a tag. No. Except, of course, it's different. Yeah, so we do have tag dot, what was it, dot something, hang on. Tag contains a yogurt tag, oh. With a symbol and args, well that's actually readable, I like that. So much more readable. Okay, so tag, yeah, we don't actually need these, I think. Variant and args, no. No, so we have the type, we already have that. We know this is an enum kind, enum type, enum layout. And we are already aligned and everything, so let's just skip this direction thing and just say this is our layout. And then in our enum layout, it has variants. Creating a tag. Oh yeah, the variant is the tag symbol. Makes sense. And args is just tag.args. This should not be a value, but an arg, which is an ID. Then instead of pushing the value, we say copy from stack with that ID. something like this. Yeah, we need to know its size. So that would be enum layout dot, I'm not sure. Enum layout dot get the layout of that field, basically. Like, hang on, args layouts probably. Dot arg layouts dot get index. Yeah, that gives us the layout of the argument, and then the size of that is what we want. Yeah, something like that. Is a symbol is not on tag layout. Oh yeah. Well, very, very true. You know, the more I'm reading this and thinking this, it probably makes sense to have another compiler stage between, you know, between yogurt and this. A compiler stage with a similar abstraction level to C, I guess, where basically we don't have to do all of this mapping. Like, what is the so currently in our transformation from yogurt to bytecode, we have to do two mappings. We have to think, how do we represent these things as types, and we have to think, how do we like map them to a stack in so that the order matches, you know. I think it makes sense to split that, to have something that is on a similar level of abstraction as C code, for example, where we don't have enums anymore, where we just have structs, you know, fields that are next to each other, and enums, or structs and unions, fields which are which directly overlap each other, and then enums are basically converted into this struct, into a tagged union, basically a struct with a tag and the payload, and like all of that is explicit in there. And we could maybe also put the padding explicitly in there, and I think that's a bit clearer than doing this on the fly. Yeah. It's just I don't know whether it's a good idea to just continue doing this for now and then later on refactor that, or just directly create a new compiler stage for that. No. I'm tending towards the new compiler stage, to be honest, because that makes debugging so much simpler also. If you just if you don't have to basically run the VM and see what happens and whether things are correct, but having like a declarative lower level language or representation of what you actually want to do. Yeah, that makes sense. Oh man. Okay, so do I do that now or next time? Maybe I'll design the stage now and the conversion will be next time. Right. So yeah, let's maybe copy the yogurt. I don't know the name yet. I'm gonna think of something. Or ask ChatGPT or something for a nice breakfast themed one. Yeah, okay, so all of the code, I'm just gonna delete that. I'm just interested in the data structures for now. Yeah, every yogurt thing, I'm gonna rename that. Okay, yeah, so the idea is that we have functions with signatures. True. And each function basically we don't have types anymore. In this case we don't have types, at least not plum types. Oh yeah, I think we have new types. That can basically be byte. Oh, hang on, let's call it U8 maybe. And U8 like this. Yeah. And signed 64, something like this. Unsigned and signed, you know. Or it can be a struct type, but not with any field names or something, just indices in the struct, basically. Then again, does that make sense? Let's maybe say, yeah, okay, for now let's do that. Okay, so a struct which then contains other such types. Or it's a union, basically an overlapping version of these types. So we have bytes, 8-bit unsigned integers. We have these signed things, and then we have structs and unions. Makes sense. Yeah. Okay. Then maybe the memory layouts also don't need to be computed on demand. We can just have one compiler stage where we convert them into something like this. And we don't even need to keep that mapping around, Oh, yeah. For the memory layouts, I was also struggling with this. Do we have basically a representation of what the memory is with structs and unions and so on, or is this a mapping between yogurt, plum types and some lower level form? And with this, this is explicit. This is definitely just yeah. Let's put padding in here with a size. Damn. Okay, so a struct will actually just have Leer types interleaved with padding. And a union will actually just be a Leer type that is a struct of a payload and a tag, which is a U8. And the payload then will just be a union of other types, which will be structs with the variance and padding in between. Or the entire thing might be padding if there is nothing. Ooh, I like that. Okay. Oh, that is so nice. And then we have the values. Okay. We don't. I think we don't need them here. I think we can just say no. Yeah. We do need to think about how, you know, how we represent strings and so on, but yeah. I like hang on with int string struct, something like this. So I think this will still not be stack based, and this will just be what will it be? Kind of it will be graph based, I think. Yeah, we don't have, at this stage we don't have lambdas anymore. We just have normal calls. And really lambdas, you know, they are just structs. A struct with a function pointer, maybe. So, you know, a pointer. And a pointer to a closure, also this. Oh, that's crazy. Okay. Okay. So what do we have? Do we have members? Yeah. We need. Yeah, we don't have values, but instead we have, you know, ints, like bytes, I guess, which are just like byte, which will be a byte, with int, which will be an int, and these are basically these right here. Yeah, okay. Then we have structs. Fair. Members, okay. We have tags. Let's maybe first remove all of the lambda things from this. And the switch should not, you know, should have, you know, a byte basically. And there's not a map. There's just a list of bodies. And depending on the byte, there's basically the index which body is chosen. Yeah, creating a tag is also not really a thing, because that's just creating a struct. Okay, yeah, we should have something like creating a union, which is not really this. Oh, yeah, struct is also not this. Struct is just that, perhaps. Do we need padding as a thing in here? Maybe. Yeah. Yeah. Okay, and the union is just basically tells us what the I'm not sure. Like, really, this is just a normal ID. Yeah. And this is getting an offset inside of some other structure. Okay. And then we don't need these anymore. We don't have lambdas, don't have tags. Nope, nope, nope. Okay. This is weird. Yeah, you know what, let's maybe, to make this a bit more graspable, I guess, let's write how code in this looks. Here, because a low level intermediate representation. This also does not exist, I think. Yeah. Okay, so like captured is not a thing. Lir param refers to lir value, but that type doesn't exist. Yeah. Also, like, is lir param used anywhere? Not really, right? Yeah. No. Okay, so the idea is that you have something like this. Main int takes an int, which is a signed thing. And then you can basically create, say, a new struct, which will not have this layout, or this thing. It will just be this. It will be next, like multiple types next to each other. Yeah, struct with, I don't know, an s something and an s something, instead of a point, for example. And this will just be a struct. Yeah. I don't know how that looks, but I could use this for structs. Why not? Yeah, a struct containing, I guess, 0 and 0. Maybe let's create a constant like 42, and then this can be the argument and 42. Yeah, like that. And then could, for example, and let's say 3 is some not sure. We've created a struct. So now we should be able to say something like this. Not offset. So basically dot member at offset 8, something like this. Damn. Maybe rename these. I'm not sure. To byte and word, I guess. Yeah. Yeah, the member at offset 8. And yeah, the size of that is a word. And then you can call something like creating and accessing the struct. Yeah, let's try to go through the yogurt. Okay, so comp time stuff doesn't really exist. We do have like int literals and string literals and so on. Yeah. And then we have this, creating a struct and accessing that. Then creating an enum. Creating and switching on an enum. That would basically be a struct. A struct with a union, which I'm gonna write like this in the byte. Foo is x equals 42, y equals like this, perhaps. And then foo dot y. Yeah, that would basically map to this. Creating and switching on an enum. So here the idea is that we have foo of the type maybe int is, yeah, we don't support type annotations yet, but we might someday. Some 5, and then we switch on that. So foo switch, if it's, I don't know, none, then we do something. If it's some int, then we return the int instead. Seems fair enough to me. Okay, so then how would that work? We would first create the struct. So creating a 5, that's the easy thing. Then creating something of this type. So something with a tag at the end and a and something in the beginning. Basically, what is in the beginning? Just some union of word, I guess. Yeah, oh, yeah, a word or padding 8. Okay, so we have a tag basically, then the payload is either one of these. I'm gonna put them in order just because, why not? Yeah. And this is, the tag is 1, let's say, and the enum is a word. More specifically, the 4. Yeah. Which means this 5 is actually gonna have the type byte, and it's gonna be 1, and then it's gonna be used there. Crazy. Yeah. So this basically creates the enum, and then switching on that would mean getting the tag out of the enum, which would be a totally normal, boring member access like this up here. So this would be 6.member at the offset 8, correct? And yeah, then we can switch on a byte that works. And that results in something, I'm not entirely sure what. Oh yeah, the enum things, they evaluate 2 words. So I think we should have something like switch on 7, which is a byte, and you can only switch on bytes. And yeah, basically if that is 0, then we do something. If that's 1, then we do something else. Okay, yeah, if it's 0, then we just evaluate to the 0. Yeah. Okay, and if that's 1, then, well, then we evaluate to that int. Ooh, so to this basically. Interesting. So this would be, yeah, just the 4. And we could say that member 0 maybe, but we don't really need that, I guess. Yeah. Yeah, I think I like that. Ooh. Yeah, we convert things to the stack-based representation anyway after that. Does it make sense to maybe turn this into more of a tree rather than this graph with IDs? Like, we definitely need IDs. For example, if you have a function call, like this is call something expensive, and we put that 2 times in the struct, then like we can't inline this call 2 times in here. Like, that doesn't work. We need local variables. But for most things, we don't actually want to, like in our thing here, we had a lot of these instructions that basically just boiled down to, yeah, you're pushing some numbers, and then pushing that same number again, and again, and again, and all of these operations that I don't think we need that, you know? Like, it would be pretty cool if we would just push the things in the order, like basically adjust the order that they were pushed in so that everything lines up. Basically allowing us to inline this into this, I think. Something like this. Yeah, this would be something of a type, I guess. So basically we reintroduce a tree. And I think also conceptually that makes sense, because first you have this user program that is explicitly written as a tree, but you don't want to link yourself to that version. You want to, we want to do crazy numbers of analysis and optimizations later on as well. On that representation, on more like a graph-based representation, that's easy to work with. But now we basically go the opposite direction. Now we have this high-level representation, and we want to go to something that's ever more low-level. So I think in that case it makes sense to go back to some sort of tree structure. Doesn't have to be the same tree structure as we had originally. You may have something like I declare local variable a as 5, and then I create a struct containing that a and that a again. And here we might actually like duplicate that into a struct that contains just hard-coded 5 and another hard-coded 5. And then in the bytecode we would just have push 5, push 5. So whether something is, is a separate node or not is not, the previous stages won't determine that and shouldn't determine that. Yeah, I think that would be cool. So yeah, I should fix the example first. I think I had this, maybe. This would, yeah, something like this. 0, 0, okay, dot member 8. Okay. So in this case, obviously, we would, before we do that, we would optimize that so that this just directly refers to the asked expression. And to the, the correct expression there. Okay. So creating and switching on an enum. Oh yeah, by the way, this should also just be inlined directly in here, I think. So we have 0 of the type word, we have 42 of the type word, and this entire thing is of the type word and word. So yeah, we access the member 8. Okay, you know what, I think we don't even need types at this point. Yeah, especially if we have padding explicitly. That is something crazy. Yeah. What? like that. Basically, a value just represents some series of bytes, and that's it. And if something can be inlined as a series of bytes, we just do that here. So yeah, initially, sure, there's the parameter on the stack, and then we build up this series of bytes. And yeah, we assign that to something. I'm sure we can do that. Though we don't really use that, but okay. And then down here we do the same thing. Yeah, things don't have types. You know, let's maybe see, this is bool, and it's true. If it's, and then basically, yeah, we check if is that true, then we create sum 5. If it's false, then we just create nothing. Oh yeah, I like that. I like that a lot. Yeah, we don't have any types. So we just have 4, which was 5, confusingly. Yeah, I think for numbers we need to specify what they are. So this is a word, this is a byte. Oh yeah, for bool we actually just have true, which I don't know, is 1 maybe. Yeah, and if something is a struct with only one field, we don't really care for that. Yeah, it's a struct containing an empty union and one field. Crazy. Okay, yeah, and then we get the member at offset 0. That would be this byte. And we switch on that. Let's just do that with this, you know? Because why not? I like this, I guess. Also fine. Yeah, and we have code for 0, which just creates a sum. So, oh yeah, no, this is the false thing actually. So, oh, crazy. Yeah, 0 means what does that do? Now let's remove that. Braces just mean struct, and that's it. Yeah. 0 means I'm not sure. Creating a none basically. So creating, padding 8. Whereas 1, the true case, means that we create some by padding 8 followed by a 0, I guess. Right. And this is 5 word followed by a 1 byte. Yeah, that's basically it. This is so cool. This is super cool. Damn. Okay, so this compiler stage. Is pretty low level. Yeah. It's no longer graph based, but tree based as a preparation for lowering to bytecode. tree-based as a preparation for lowering to stack-based bytecode. But mainly tree-based. You can still have local variables. Yeah. Types no longer exist. Instead, each expression corresponds to a slice of bytes. Yeah. For expressions to be compatible, such as branches of a switch, they just have to have the same length. Hell yeah. Oh, hang on, and alignment. Yeah, okay. Yeah, I guess alignment kind of makes things weird. I don't know how that's gonna factor in here. Structs have been converted into runs of expressions shown using curly braces. Yeah. Enums have been converted into unions, into tag unions. Yeah, that's basically it. To do alignment. Yeah, you know what, we might actually do this without any alignment checking first, and then worry about that later on. Yeah, I do like that. That's pretty cool. Yeah. To do heap. To do reference counting is something that we need to put into the code somewhere, and I think this would maybe be a good option for that. Or maybe an extra compiler stage in front of that. I'm not sure. Okay, yeah, but this looks super nice. So this will basically be the stage above the bytecode. You know. Yeah, whether we add stages before that, maybe. But that's pretty cool. I like how, you know, the compiler pipeline at first gets, like, the parser is pretty robust, I think, and pretty stable. And then, you know, figuring these stages out, like, there are some vague things which are not set in stone and still require exploration. But then at the end, it gets, like, the bytecode, I think, is pretty solid now. And the stage above that would also be pretty nice. Like, from you know, just from a design perspective. Sure, tons of it are not implemented yet, and it doesn't work yet, and so on. But just from conceptually, these are like very nice, clean, coherent abstractions, I think. Yeah, okay, so let's maybe formulate this into types, and then let's stop for today. Okay, so yeah, this maps signatures to functions. Sure. A function is something. A list of expressions and a body. Is that correct? could even like represent this as we usually do, you know, like just having IDs and then a big list of all expressions. But I want to make a distinction between these locals that can be used multiple times and these things which are entirely like strictly tree-based. Basically the expressions in the yogurt which are only used one single time. You know, like here for example, we switch on that and then we would then push that and pop that underlying thing. Or here we create a new thing on the stack currently, and then we create another thing on the stack, and then for the call we push the arguments to the stack, and then, you know, we have the call result as another thing on the stack. But in reality these are only used in this call. They are only used one single time. So I think it would be better if we just put them, like push this to the stack, push this to the stack, then call that, and that automatically consumes them, and that's not a problem. So we don't need to copy as much things on the stack. Yeah, that's why I like this, you know, basically tree structure where we inline things basically, instead of having IDs all over the place, because then when going through that we don't know how often IDs will be used later on. And it allows us to, you know, basically put these into a shape that makes sense, in an order that makes sense. Yeah, once we have a tree, that's pretty easy. For a graph, it's kind of difficult. Yeah. Okay, so I guess let's see, Lear Fun is here. That is here, yeah. And we basically have these kind of top level expressions, which I don't really like, you know. Yeah, let's maybe instead I don't know whether that makes sense. But these are not expressions, okay? These are like locals. I'm gonna give them a different name. Local variables. And they have IDs, and they are just expressions here. The expression, okay, yeah. And then we have the body, which is a Lear body. Yeah, also makes sense, perhaps. Yeah, this is just an index into that list. But actually, let's not. We don't use that often. That I think type for that makes sense. Okay, so the body. A body has. Oh, a body does not have parameters. Like for example, the surrounding body. I would say that we just create some locals for that just magically exist for the function. And for these switch case things, you would actually have to unwrap, or like, you know, get a member of the thing that you switched over. So this is not, like, bodies don't have parameters in the general sense. And bodies don't even bodies have? I think just expressions, yeah. And these are Lia expressions, like actually owned expressions in here. And it returns some Lia expression. Oh, hang on. No, it's just going to evaluate to the last one automatically. Yeah. Which means that Lia body just gets inlined there. Okay, yeah, expressions don't have types anymore. All these things. No, they are kind of useful here, I think. Well, yeah, these are basically Lia expressions instead of this. Yeah, the Lia expression can be a parameter. And this is basically where we need a type. This needs to be a type, yeah. I see that. Mm-hmm. Mm-hmm. Oh, we could say that every expression has a type, you know. Yeah, maybe that makes sense. Yeah, uninitialized, like, why no? We do have padding, which I think is the closest thing to that. Padding, we have byte, we have, let's call it word maybe. Yeah. You know, ints of different sizes. In C, ints are 4 bytes. In other languages, they have different length. I think it makes sense for word, which is not even recognized. Usually, the word refers to the size of your instruction of addresses, you know. But then again, in most assembly languages, because they grew organically, word usually refers to like 2 bytes or something, 4 bytes or something. I think 2 bytes, and then you have double words and quad words. It's all a mess. Yeah, here maybe let's write 64 bits, 8 bits. Yeah, okay. So we can have struct expressions like this. Yeah, which will just be a slice of expressions actually. Mobs. And unions don't really exist, to be honest. That's crazy. You know, like this. No, we don't need that. Unions only get created implicitly using the switches. Amazing. Amazing. Yeah. Okay, so we have unions. No, we don't have unions. Yeah. We have members, which have an expression and an offset. Beautiful. And then we have a switch. Makes sense, I think. Yeah, it switches on a byte, which will just be a Lia expression. And it has cases, which is a slice of bodies, aka slices. Nice. Yeah, and we do need some ID reference in here, so that you can what's it called? Refer to local variables. Yeah, okay. I think all locals will be in here. And we will actually, okay, yeah. Let's say we have a Lear body. That makes sense. Lear body, and then this will also be a Lear body. And what a Lear body has is just locals slice of Lear ID into this locals thing, slice of int. Yeah. And it will have basically what it evaluates to. So returns. Yeah. And there it has the Lear expression actually. Yeah. Cool. Cool. Yeah, and this local can, yeah, okay, I guess local ID makes sense. Like, but let's call it local ID. Okay. With the index, it does an int. Yeah, I'm gonna put these up there. Okay, yeah, then we have members. Okay, we have switch. Okay, yeah, and we have Lear calls with a function. And the arguments are expressions, because of course they are. Oh, no, the argument is a single expression. Oh, that is amazing. That is amazing. Okay. I love that. And yeah, we have the instructions. Also with a single argument, I think. No, I think these will be different things. Hang on, what are our instructions? Maybe it makes sense to have them. I guess. I don't know. Let's say arguments is like, for now let's say the expression, because I don't want to do anything like yeah, I don't want to do any layouting on the fly. Like this should have all data layouted, like memory layout should be fixed and so on. So the expression refers to ID, and indeed this should be local ID. Yeah, to do what to do with this, because I tend towards actually like copying these basically and pasting them in here, and yeah, what I'm not sure. I am really not sure. And still, like, yeah, alignment is a big thing, and heap is also, need to figure that out. But still very, very cool. Yeah, I think I'm gonna end it there today. Kind of a anticlimactic ending. We basically tore off the end of our compiler pipeline. We implemented memory layouts, which is like pretty insane. Yeah, we have a bytecode which kind of works. The bytecode itself is also pretty simple. And look at that. The lambda call, we can just remove that, because there is no concept of lambdas here anymore. Boom. And yeah, this is not necessarily from the same compilation unit. Calls another function to do runtime known. Okay, yeah, maybe we do need an extra instruction where the address is not comp time known, but only at runtime. And then we, for lambdas and stuff like that. Yeah. Let me commit this. Yeah, that's fine. Yeah, I guess design new, many things actually. Like remove lambdas from VM. Then here we have some stuff and implementing tags. Start clear. Okay. Yeah. To be honest, I really like this low-level stuff. Like especially this the design that I came up with in the end. Of having local variables, but basically the majority of things will already be like tree expressions. Which allows us to like really easily convert these into bytecode instructions later on. And I do think that having an intermediate representation here is like that totally makes sense. Yeah. Okay. I love this. And we don't even have to generate this directly. We can just say in the beginning, everything is a local. Like every expression from the yogurt gets loaded to a single local thing. That looks like the structure could look very similar to what the yogurt looks like currently. But then we do crazy things. Then we inline locals, and we, I don't know, like we see, you access the first thing of a struct. Well, then we don't actually need the, we don't need to change something about the struct. We can just use that directly. And yeah, all this inlining and stuff will be pretty cool. Yeah. Okay. Yeah, kind of anticlimactic. But I think we have something fun to implement next time. And it would be pretty cool to see this working. So I guess see you then, and goodbye.